is viewed on an oscilloscope.
Okay, it's 8 a.m. Central European time. So let's start the morning session of the formal theory development part of the ICHEP conference. My name is Jaroslav Trnka, and I will be a session chair today. So I'm sure we will hear a set of very interesting talks. So let me just remind you some rules. So please, everybody stay muted during the talk. If you have any question, raise your hand in the participants option in Zoom, and I will get back to you. For speakers, please, after sharing your screen, your slides, please also turn on your camera. The time is 25 minutes for talk and 5 minutes for questions. And I will be sending reminders in the chat to speakers about the remaining time. So please check that. So without further ado, let me introduce the first speaker, who's Johannes Henn from Munich. So Johannes, please share your screen and turn on your camera.
Sure. Good morning, everyone. Let me see if I can manage that. So I'm sharing the screen with my slides, hopefully. Okay.
Excellent. Yeah, if you can do the full screen.
Can you see the slides, Jaroslav?
Yeah.
Good.
Do the full
Screen view. Okay.
Excellent. Okay, so Johannes will talk about the novel methods for calculating Feynman integrals and applications to QCD. Please, Johannes.
Yeah, thank you, Jaroslav, for the introduction, and good morning to everyone. Before I start, I would like to say, please feel free to ask questions during the talk, because I think this is a bit of a broader audience than usual, and it would certainly help me to get some feedback and possibly explain better if you ask questions during the talk. I think there's a way of writing in the chat that if you have a question, and then I think the host Jaroslav will alert me to it. All right, so the topic is about novel methods for computing Feynman integrals and then applying them to QCD processes. I will mostly focus on the methods for various classes of integrals, and then it will become obvious what kind of physics they're related to. So let me start by recalling that Feynman integrals are very important in quantum field theory and in high energy physics in particular. They're required to compute physical observables. Here's some examples. The Higgs discovery is an important one. Of course, that's a huge achievement of the experimental community, but also a big theory effort went into it to compute, on the one hand, the background, and then also the contribution from the Feynman diagrams involving the Higgs boson. Perhaps one of the best examples for high precision calculations using Feynman integrals is the anomalous magnetic moment, where here there's a representative one loop diagram, but in fact, this has been pushed to the 4 and 5 loop order. And in fact, as far as I know, at least the 4 loop order is actually required to match the experimental precision. So our ability to evaluate those Feynman diagrams and the underlying Feynman integrals is really important from a physical point of view. Interestingly, there has been also and continues to be a lot of fruitful interplay with mathematics. On the one hand, that's really fascinating. And on the other hand, that gives us a lot of new tools and insights for how to approach a problem. So there are several challenges, in fact, which have to do with different aspects of the problem. One is that we're typically interested in problems that depend on a number of scales like masses, energies, scattering angles, which means that then the functions we have to deal with depend on multiple variables, and that is technically challenging. Moreover, if we want to in many cases, we need to match experimental precision, and that means that we need to go beyond the leading order and even beyond the next to leading order, which means that we often have to deal with multi-loop integrals. I just mentioned the anomalous magnetic moment. Here is an example of a free loop integral. And technically, that means that the special functions we're getting, they are typically iterated integrals and multifold iterated integrals. Finally, beyond the one loop order, we also encounter non-planar diagrams, and they have a much more intricate analytic structure. So I think these are essentially the three technical challenges that we have to overcome. And this is especially so at beyond the one loop order, where there's still many things that are unknown. So to phrase it in an equation, the problem we're facing seems very simple. So usually the Feynman diagrams, they give a loop integrand, which is a rational function of the external momenta P and some loop momenta K. Then we have the four-dimensional integrations, one set for each loop. And after we've done the integrations, we get our functions, which called F, which just depend on the external momenta in some Lorentz invariant way. And these are typically special functions, could be logarithms, dilogarithms, and generalizations thereof. We call them transcendental functions. So those we'd like to determine, and there's some general question for given Feynman integral, what kind of special functions can we get? Related to this, what physical singularities do they have? And how can we, given a loop integrand, how can we make this map efficiently to go from the integrand to the function f? So one of the main methods, or I would say even currently the main method for answering this question has to do with differential equations. The idea is to derive directly differential equations for the function f. So in other words, to understand how it depends on the external variables. And this has the big advantage that one does not have to worry about all the details of the loop momentum dependence at the intermediate stages. So one directly tries to formulate some equations which are valid for the function f. However, in doing so, it turns out that the properties of a loop integrand of this nice simple rational function are very important and can give us a lot of insight. So before going there, let me mention one important technical point, which is that I wrote the integrals in 4 dimensions, but typically in physics we encounter certain divergences, ultraviolet or infrared. And a popular way of dealing with them is to change the dimensionality and to introduce dimensional regularization in this way. It makes things a bit more complicated, but it's very useful. Physically, when we get the functions we have then depend on this parameter epsilon, deviation from 4 dimensions, and we can write a Laurent series in epsilon. And physically, what we want is we want to expand this essentially up to the finite part, which, for example, could represent a finite cross-section. And the price we have to pay is that we also compute these poles. Now, mathematically, it's actually also quite interesting and can be useful because it can serve us as an organizing principle for this expansion. And it turns out that if we choose our integrals in a clever way, then this expansion has very nice properties in the sense that the each order in epsilon corresponds to a more and more complicated function. And specifically, these functions fk, they will correspond to iterated integrals where k tells us how many iterations we have to do. And so this turns out to be extremely useful in calculating the answer. So now coming back to kind of perhaps less technical way of presenting the method is the following. So I told you that we're interested in differential equations for the functions f. And it turns out that for any Feynman integral, one can always derive some differential equation. This is typically some nth order, so higher order differential equation. It's called a Picard-Fuchs equation. And so it turns out that it's useful to transform this, and this is something one can always do when you have an nth order equation. You can always transform this into a system, so a matrix differential equation, which is first order. So this is something that we can always have for given Feynman integral. So now you might think, well, if we have a first order equation, maybe we know something about a boundary condition, then basically the problem is solved. Unfortunately, it's not so easy because this equation is typically very complicated. So it depends in an extremely complicated way, typically on the dimensional regularization parameter epsilon, and also on the kinematic variables. Could be one kinematic variable or many variables. So although in some sense mathematically this defines the function, it's not very useful. And so some further work is needed here. And so this is where some new insights came in. And the idea is the following. The idea is to think, well, at the end of the day, what are the functions going to be that we'll get? I mentioned earlier, we expect some special functions like logarithms, dilogarithms, and so on. So these are typical special functions that you encounter in mathematical physics. And we know each of them can be defined from some simple differential equation. And the same is true also for the generalizations of these special functions that one encounters in higher loop integrals. So the idea is to say, well, we always have some system of equations. We expect that the final answer will be given by some nice special functions which satisfy simple differential equations. So the question is, how can we transform these complicated equations to some simple equations where we can read off the special functions that appear in the final answer? So that's the idea. That's what we want to achieve. Now, okay, this is the philosophy. How does it work in practice? Now let's go to some equations. So the first slide that I showed was the generic complicated form. So let's say we have some function, Feynman integral, which depends on one kinematic variable x and the dimensional regularization parameter. Then what I said just previously is that you always have a first order system. So this f now, the first element would be it will be a vector. First element will be the Feynman integral we're interested in, and then there's various kind of auxiliary objects. And then on the right-hand side, we have some n by n matrix, which is in general has complicated entries depending on x and epsilon. And now what we can do is we can think of a transformation of a basis where we change this vector f in some invertible matrix T, go to some new basis, and then the matrix A actually changes as under gauge transformation. And now it's clear that there's a lot of freedom here because you can choose the matrix T in many possible ways. And depending on what you do, this may make the matrix A more complicated or simpler. And so the insight I told you about just now is that it's possible to reach a very simple form for A. And this is what we call a canonical form. So in this example of one variable and under some assumptions, the canonical form is the following. So after some suitable transformation T, you expect to find this form, where now what has changed is that there's a very specific form of the right-hand side, where some things happened. Here there's a sum over k, and you see some values xk. These are singularities of the Feynman integral. And you can see that in this form, all the singularities are now very explicit and just have simple poles. That's one special feature. And the other special feature is that the epsilon dependence is also extremely simple. It just appears as a factor on the right-hand side. And this, it turns out, is what helps us to have this very organized Laurent expansion, where if we solve for this function f, each term in the expansion will be some iterated integral and always increasing in difficulty by one step. So the order epsilon k term in the solution will be a k-fold iterated integral. And that's in this form, this is obvious thanks to the special epsilon dependence. Maybe I should pause to ask the chairperson if there's any questions, or if people have questions. Okay, nothing so far, I guess. Okay.
Don't see any questions. Yeah.
Let's proceed. So it's early in the morning. So anyway, if someone has a question, please don't be shy. All right. So this is the idea, and in fact, there's been a lot of work on implementing this. So this is kind of the what we want to achieve. But of course, an important question is how do we do it? And there's actually been a lot of work on this problem and a lot of progress. But at the same time, so I won't review all the progress now. So essentially, what one thing that one can hope to do is, so one sees in the final form, the answer has this simple property that I just mentioned, that each function has this, is an iterated integral of a certain degree. We also call that transcendental weight. And when we call these functions, we say that they have uniform weight. I'll abbreviate this by UT. So if you happen to know a set of Feynman integrals that have this property, then actually it's guaranteed that you get this this canonical form. So a lot of work has gone into finding UT integrals, and in fact to find a complete UT basis for a problem, because in that case, then you're guaranteed to find this simple equation. Now, as I said, there's been a lot of progress there, but I think it's fair to say that it's still a complicated problem. And in particular, this is complicated when you have Feynman integrals, or a set of Feynman integrals with many, where many integrals are coupled at the same time. So for example, let's say in a typical problem at 3 loops, you might have the order of 50 integrals. If you have a 4-loop problem, maybe you would have even 500 integrals coupled at the same time. So this is the size of the matrices that you can imagine in the previous problem. That's one difficulty. And if you remember in the beginning, I said another difficulty is if you have many kinematic variables. So my example was for one variable, but there exists a multivariable generalization. And this is a big technical difficulty. So most previous methods, they require us to find the knowledge of the complete UT basis. And then, as I said, then we have this simple form. But now in some new work, we propose a method, we extend a previous method, which actually only requires one of the integrals to be nice, to have this UT form. And then we can apply it and derive the transformations in an algorithmic way for the complete basis. So you can see that if you think of a problem with 500 integrals, this is of course a huge advantage, because you don't no longer need to find immediately the 500 nice integrals. One would be enough, and then the rest is done algorithmically. And indeed, it turns out that this method does apply nicely also to larger matrices. I think 500 would be an extreme case, but it's possible. And also importantly, it applies to multiple variables, which for some of the previous method is at least challenging. So in fact, this idea is not new. It's a generalization of something that was worked out by these authors, Höschle, Hoff, and Ueda. And their idea is to come back to this first order equation. They say, well, if we have one integral which satisfies this nice UT property, then it's first order. To go back to the nth order differential equation. So they say that if there's one integral which has this nice property, then we should see this in its nth order differential equation. And that, in fact, in that equation, there's a lot of information that we can use to find the basis transformation. And they worked this out and demonstrated it essentially for small systems of integrals, having systems of 2 or 3 coupled integrals, where they knew one integral and then derived a good basis for the other integrals. And they also outlined a general procedure. So what we did in our work with Christoph Glapper and Kai Jan, who I think is also online in the session, we took that as a starting point and formulated this method in a matrix form, which allows us to apply it systematically to larger systems of equations. And we also showed how one can systematically solve the resulting matrix equations, and in fact formulated it in the form of an algorithm. And this is a public algorithm that's available here on GitHub. So now in the remaining time, I think I have a few technical slides explaining this algorithm, but I think in view of time and given that it's kind of a more broader audience, I will skip the more technical slides. And indeed, Jaroslav tells me that I have 5 minutes left. So instead, I will go directly to show you some applications. So what is this algorithm good for? What can it do? So allow me to skip a few slides. As I said, algorithm is publicly available. Now let's see what it can do. So here's a first, this is, if you wish, a benchmark example. So these are free loop integrals for 2-to-2 scattering. So on-shell scattering processes. If you go through the kinematics, turns out there's one non-trivial and dimensionless variable x. This is a case where if you look at this free loop ladder diagram, you have 26 coupled integrals. If you look at the so-called tennis court, you have 41 coupled integrals. And in this case, the canonical equation, it takes this form. So the right-hand side, it has this form. There's these singular points at 0 and -1 and infinity. And so our starting point is then just one uniform weight integral, which we get by some auxiliary analysis, one of the previous methods I mentioned earlier. And then we just put that into the algorithm, let it run, and it finds for us the canonical form. Okay, so this is very nice. It reproduces very effortlessly essentially what was done in this paper in 2014. Now let's look at essentially a higher loop generalization of this. So this is now similar kinematic process, but 4 loops. And here we look at this 4 loop integrals, but now we restrict ourselves to the cut. So what for the moment, what this means is that one replaces the propagators by delta functions. And this really allows one to focus on the coupled system on the cut. So there's one important difference to the previous case. In this case, so one has the full 41 by 41 system, but really one can kind of decompose it into blocks. And in this case, the biggest block has four integrals at a given time, while now there's 8 integrals at a given time. So then we let our algorithm run on this cut, solve this, and then solve it for the full system, which here has 19 master integrals. So one might think, well, this 19 is less than 41, but actually it's more complicated here because there's this intrinsic coupling of the 8 integrals. And anyway, this also runs through very nicely. Here in this case, we also demonstrate how to fix then the boundary constant and to solve for the integral analytically. I think as far as I know, this was not known before, so this is a new result. Here's the answer written in terms of some special functions that are quite common in this literature. Okay, now moving on. Still staying with a problem where there's one non-trivial variable, but now increasing the difficulty from planar for loop integrals to now something non-planar at the for loop level. So that adds another layer of complication. The physical problem here, and in addition, many coupled master integrals, in fact. The physical problem here is one arising in heavy quark effective theory. So these are integrals, so-called HQET integrals, where these double lines represent massive particles and which emit some soft particles or exchange some soft particles, which are given by the other lines. So this is something that's important if you wish to analyze soft and collinear effects in scattering of massive particles, for example, TT bar production. And previously this had been studied up to 3 loops, and now we computed non-planar for loop integrals, which are relevant to the for loop cusp anomalous dimension. And so here, as I said, this is more complicated because it's non-planar. And now there's even in this particular sector, there's even 17 coupled master integrals. So this is, as far as I know, something which had not been possible with any of the other approaches to the problem. But here, with our new algorithm, it just runs through easily. Takes 10 minutes, I believe, on a laptop computer, and then one finds this again the simple canonical form. As I hinted at, we then went on and computed actually not just this sector, but a whole set of for loop integrals, including more propagators, and applied it to the for loop cusp anomalous dimension. So there's this very recent work where we compute for the first time the matter-dependent Quartic-Casimir terms in the for loop cusp anomalous dimension. In particular, this also then gives a full QED result for the for loop angle-dependent cusp anomalous dimension. Okay, but in view of time, I will not say more about this, but let me just come to my final example, final application. So the cases I showed you before were in the single variable case. So now this is, now importantly, our method also works in the multivariable case. And these are integrals which were just computed roughly 1 year ago. So these are relevant for 2 to 3 scattering. These are 2-loop integrals, non-planar integrals. These are extremely complicated because they depend on 4-dimensionless variables. And there's also many integrals coupled in the top sector, many singularities. Again, with the input of one UT integral, algorithm runs through, in this case, just in 5 minutes. All right, so now since I have less than 5 minutes to conclude the talk, let me just kind of summarize here what I said. This is kind of an overview of applications of our algorithm. So you see that it works in different cases. One common feature is that in all cases the timing is quite favorable. In the most complicated case, it took half an hour. you can see that in most cases, in first 4 cases I showed you, there was one kinematic variable, but there was various degrees in difficulty as far as the size of a matrix is concerned. So we had both very rather large matrices and the individual sectors small, but we also had cases, and this is what's really challenging, when you have many integrals coupled directly. And as you can see from the timing, this was not really a problem. Also, I mentioned in passing that we extended this actually to full for-loop HQT integrals, and that's a problem where we really have we had to solve in the hundreds of master integrals. Now, it's also important to look at the memory requirement. And so if you look at these numbers, they may seem large until you notice that this is the unit, it's actually megabytes. So in terms of modern computers, this is really almost nothing. So certainly we're still very far away from a bottleneck here in terms of memory consumption. And then finally, we had this case with 4 kinematic variables. So I think that's very important to highlight, because that's something that other methods certainly struggled with if you have multiple variable dependence. And of course, physically, that's something very important, especially as we look at processes of many particles, or we want to keep mass dependence. So to conclude, we provide a new automatic tool for calculating differential equations for Feynman integrals. And this removes an important bottleneck in the calculation of the Feynman integrals. I mentioned that the method is efficient, works for large systems of coupled integrals. That's something new. And also it works straightforwardly in the multivariable case. I did not focus on this so much, but it's also as a corollary, there's a useful feature that if you have one integral that you think has this nice UT property, but you're not exactly sure, our algorithm can also serve as a check of that property. So with this, I'll conclude, and thank you very much for your attention.
Thank you, Johannes, for a nice talk. Any questions or comments? So I have 2 questions. So one, for example, unit dependent variables or other properties, any way how to inject into your algorithm? Because this is very general algorithm.
So Jaroslav, the transmission was not so good. I heard part of your question. You would like to, you're asking if I can add in some further information, because what I presented was quite general. What if we have more information? So I did not hear exactly what you asked, but let me answer something that you might have asked. So I said that the information of one uniform weight integral is sufficient in principle, and then our algorithm can run. Now, in some information, actually, situation is much better, especially because our method can be married with some of the other methods. And so if we know more than one UT integral, let's say we have a problem, we need hundreds of integrals, but we know a few. I don't know, maybe we know 100, we need 500. Then we can use that information, and it simplifies our life. It can be coded in, and then essentially the transformation matrices we need to find become easier. And so in this way, you can recycle known information. Similarly, if a good strategy is to run this algorithm first on cuts and try to, so these are these coupled sectors that I was speaking about, try to transform them into canonical form. And then once you've done that, you use that information, but then you apply the algorithm to the whole system, where essentially you then fix also the off-diagonal parts. So okay, I've answered something. I hope there's some cross-section of what you asked, Jaroslav.
Yeah. Okay, great. There are no more questions. Thanks, Johannes, again.
Thank you.
For a nice talk. And we move to the next speaker. So can you stop sharing slides? Great. Mm-hmm. So the next speaker is Kayan. Can you please share your slides? Okay.
Hello, everybody.
Okay.
Can you hear me?
Yes, yeah, we hear you well. So the next speaker is Kayan from Munich, and we'll talk about correlation functions and event check. Please.
Good morning. Thank you very much for the introduction. Today in my talk, I will try to introduce and explain a method for computing event shapes from correlation function. The work, the talk is based on recent works on energy correlators with Dmitry Chicherin, Johannes Hahn, Emery Sokachev, and Alexander Ryboedov. I'm sorry. Oh, okay, thanks. So the event shapes defines a class of collider physics observables that probe the structure of energy momentum flow in the final state. They could either characterize global geometry of hadronic final states or probing multi-prong structure within a jet event. In all these cases, the event shape is a differential cross-section, and it takes the form of a distribution function in a one-parameter space. We are interested in the case where this one parameter is the angle between a pair of particles that has been detected in the final state. And the differential cross-section is weighted by the by the energy of the detected particles or by their charge. This essentially defines a angular distribution of energy or charge flow, which are called EEC or QQC. So EEC is one of the earliest measured event shape in E plus E minus annihilation. At tree level, the final state kinematics has two variables. Therefore, the kinematics forces the angle between the detectors to be 180 degrees. Therefore, the first non-trivial perturbative order starting at one loop. The leading order analytic results was available since the 1970s and is given as a function of a one variable zeta, which is defined as 1 minus cosine of the angle between the detectors divided by 2. So the standard method of computing EEC, just like the other observables, is by integrating the phase space over the squared of the on-shell scattering amplitude. But what is special about EEC is that its measurement function is fully differential in the angle of the detectors, and therefore the measurement function is and can be written as the so-called energy flow operator, E, acting on the final states. So this connects very nicely to the alternative definition of EEC in terms of a 4-point correlation function involving the local source and two energy flow operators, which are local operators sitting on the celestial sphere at the future non-infinity. In this regards, EEC is a central object in both particle phenomenology and the formal study of conformal colliders. So in recent years, due to development on the formal side, there has been renewed interest in the study of EEC from various aspects. Nowadays, it has becoming one of the only event shape observable that has been computed beyond next to leading order in QCD, and is Precisely, it is especially suitable for phenomenological application to determine the strong coupling constant or to probing the precision jet substructures. The event shape are singular in both angular points, where the angle between the detector is close to 0 or 180 degrees. These are interesting topics on their own and has been studied in the framework of effective field theories or by studying certain OPE limit of the light ray operators. And it is also possible to generalize the definition of EEC to multi-point energy correlators, where the event shape is the distribution of multiple, in terms of multiple independent angles. And this observable has the potential of becoming the building block for computing a general class of physical cross-sections. In all these projects, the perturbative analytic result is playing an important role for making advances, since having an analytic result which contains rich information provides valuable theory data to test new ideas. So computing event shape analytically at high loop order has a major bottleneck, which is the phase space integral. It is divergent and difficult to optimize at higher loop order. But thanks to new insights from similar study of similar topics in maximally supersymmetric series, we found a novel method for computing the event shape at higher loop order in a way that avoids, that bypass phase space integrals and avoids infinite divergences. And this method can be directly applied to event shapes in QCD, which was demonstrated in recent work. This inference and finite novel method benefits greatly from the connection between EEC to correlation functions. And in particular, EEC in the generic CFT can be built upon the 4-point conformal correlation functions involving the local source O and 2 stress energy tensors. And this represents the energy colorimeters, which are sent to the future infinity and integrated over its working time. In this setup, there are no onshore objects involved and therefore no infrared divergences by construction. And the phase space integrals are now replaced by certain off-shell conformal integrals to compute the correlation function. And in addition to that, we need to do a twofold manifestly finite integral over detector time. But in all these steps, we do not need any regularizations, and the calculation can be carried out in four dimensions. So let me briefly summarize what we did with this approach to compute the EEC in NX4 supersymmetric series at next to leading order. We consider a process sourced by the half BTS operator, which is a protected operator analogous to the electromagnetic current in QCD. Then we apply the conformal symmetry in N=4 super Young mills to relate the energy flow to scalar flow. And in the end, we only need to consider a 4-point correlation function of identical scalars, and then carry out a twofold integral of the detector time, and then do a Fourier transform to get the event shape. And in particular, this 4-point correlation function is given explicitly in terms of polylogarithms, which depends on 2 cross ratios U and V. So the most non-trivial part of the correlation coming from getting this integrated correlation function by carrying out the time integral. So in this formula, the integrand we should take as a Weidmann function, which is the Euclidean correlation function analytically continued into the Minkowski space. It is a multi-valued function when the detectors are in time-like separation with respect to the source. By studying the analytic properties of the Weidmann function, and applying Cauchy's theorem, we were able to convert a twofold contour integral over the detector time as the integrated double discontinuity along the branch cut. And this double discontinuity is a single valued function, and its integration over it can be done, carried out algorithmically. So in the end, in this way, we obtain the fully analytical result as 3-loop order for the event shape, which we determine the function space involving harmonic polylogarithms and manifestly finite elliptic integrals. And in addition, we did some close study onto the endpoint asymptotics of our 3-loop result. So in the collinear limit where the angle between the detectors is very small, the event shape is governed by the collinear splitting, and the divergence exponentiates to all orders and governed by the announced dimension of a spin 2 of a twist 2 spin 3 operator, and we extracted this announced dimension to order RFS to the cube. And in the opposite limit, where the angle between the detector is close to 180 degrees, a leading power on the event shape admits the standard pseudo-cofactorization. And from our 3-loop result, we extract the hard functions and collinear announced dimensions at the desirable order that is useful for the N-cube LL resumation. And in addition, we also expanded our analytic results to subleading power in the back-to-back limit. And we found some interesting new structures. So in particular, the leading log series at next leading power is now a double factorial sum up to 3-loop order instead of the standard factorial sum. This suggests that the subleading power resummation is not described by the standard pseudocov log, but a dozens, but described by a dozens functions. This is evidence that there exists multiple subleading power effective operators which mixes through the RG evolution. So these are all very nice results, and due to the thanks to the efficient new method that we developed. The next natural question to ask is that is it possible to generalize the approach to study event shape in a generic CFT or even in a non-conformal theory where the correlation function is not available? So to answer this question, we conducted the proof of principle study to compute a one-loop charge-charge correlation in QCD. So the QQC is, the definition of QQC is very similar to the EEC, where we just replace the energy flow operator with two charge flow operator. And the event shape can be built upon the correlation function of 4 identical electromagnetic vector currents, and 2 of which represent the local source, and the other 2 represent the detectors which measure the charge flow in the final state. So this is a very nice toy example to study event shape in QCD at the level where it can still be treated as conformal. Indeed, the conformal structure of this 4-point correlator is not so complicated, and it allows us to test whether our approach of computing correlation functions and implementing time integration can be applied to QCD. The validity of the approach is guaranteed by the IR and UV finiteness of the event shape at one loop order, which is the loop order that we considered. In particular, the complication due to UV renormalization can be avoided because we're considering the operator, which is the conserved current, and the effects due to the running of a coupling does not play a role at one loop order. Therefore, we know that the correlation function that we need to compute must be a finite four-dimensional objects, and we can apply the tools developed in the study of conformal correlators in supersymmetric series for this calculation. So in the first step, we need to learn how to compute Feynman diagrams in coordinate space. For example, we can write down a certain relevant Feynman diagrams, and then this is a one-loop diagram. But we realize in position space, we need to do a 2-loop integral over these internal interaction points. And the better way of doing this calculation is to use is to use the method of Lagrangian insertion. In particular, the one-loop corrections to a 4-point correlation function can be obtained in the following way by taking derivatives of the path integral with respect to the coupling. And therefore, the one-loop 4-point correlator can be related to a 5-point correlator with one additional Lagrangian insertion point, which needs to be integrated over in the end. And it turns out that this 5-point function is much simpler than the 4-point function that we started with in the following sense. So you can see that in almost all types of diagrams, you can identify a certain T-shaped diagrammatic building block. And you can isolate this block and to do some studies. It turns out this integral, this 3-point integral is rational because the external derivatives hitting on the external points localize the integration over the insertion, over the internal interaction points. And in fact, this integral can be related to the well-known conformal integral in whose answer is a rational function completely fixed by conformal property. So for all the diagrams which can be built upon the T-shaped blocks, we find a rational and finite expression, which is of a 5-point function, which needs to be integrated later. And for the other type of diagrams, which can be built from a different building block, we played a similar game, and we found the expression of this propagator type of building block, which is also finite and rational. So in the end, putting together all the building blocks and all the diagrams, we find the finite and rational functions living in the four-dimensional space-time. And then we explicitly check that this integrand of a 5-point function is conformal and obeys current conservation. And the next step is to carry out the integration over the Lagrangian insertion point. And this step can be done more or less in the standard way by doing tensor reduction and IPP reduction onto a set of mass integrals. And in this case, are the bubble and one-loop bubble and 3-mass triangle and 4-mass box integrals. In the end, we find that the divergence on the bubble diagrams are all canceled and triangle diagrams cancel out. And the one-loop of correlation function can be, in the end, be expressed in terms of a linear combination of block-Wegener dilogarithms coming from the box integrals and the logarithmic functions coming from the bubble integrals. And here the coefficients R's are polynomial tensors, which are homogeneous in 4 points and carrying Lorentz indices of the 4 external points. So we indeed found some better representation for these polynomial tensors by matching with the conformal answers that we wrote down. And in the end, we write the final answer for the 4-point correlator in terms of the polylogarithm, the differential operator acting on polylogarithm functions combined with 54 different conformal tensor structures. So this finished the step 1 of our calculation, which is to obtain the 4-point correlation function in Euclidean space. And this correlation function is it takes a very non-trivial, complicated form, but it contains very rich information. And for our purpose, we only need to extract the part of these informations and apply it to the study of collider physics. So in the second step, we take the limit by sending the detectors to the future non-infinity. We find that doing this by taking the detector limit greatly simplifies the structures of the polynomial correlation functions. And then after this, we contract indices among the Lorentz indices among the two sources. And And in the end, we can write the 4-point correlator as in a very compact form, which can be written as a second-order differential equation acting on the block-regular dilogarithms. Here, these little r functions are given by the rational function of the cross ratios u and v and the one additional variable gamma. So next we the next step is to implement detector time integrals. This step is very similar to the calculation performed in the supersymmetric series. So basically, we first obtain the analytically continued Wyman function from our expression of the 4-point correlators. And this function developed branch cut when the detectors are time-lag separated from the source. And we located the position of this of the branch cut in the space of the retarded time of the detectors. And then we need to explicitly carry out the contour integral over the detector time from -infinity to infinity. So now note that the detector time dependence are all encoded in the two cross ratios. And then by applying a Cauchy theorem, we can wrap around the integration contour around these two branch cuts. And the contour integral can be reduced to integrated sequential discontinuity taken with respect to the detector times. But since the detector times dependence are all encoded in the cross ratios, these operation is amounts to taking the so-called double discontinuity with respect to one of the cross ratios, V. And then in the final step, we arrive at the integral representation of the event shape in terms of integrated double discontinuity taken at the point where V is equal to 0. The integration, so the double discontinuity acting on the correlation functions gives us a certain finite distributional terms which can be readily integrated over. So carrying out these integrals explicitly, we arrived at the final result of the event shape, which fully agrees with the momentum space calculation. So let me briefly summarize. From this exercise, we can see that the position space method that we developed for supersymmetric, for event shape in supersymmetric theory can be applied to study event shape in QCD. So in this one loop exercise, you might not see that how powerful and efficient this method is. But let me tell you that at higher loop order, it is highly possible that this method has an advantage. So let me explain that n to the Kells LO, the position space calculation involves a k+1 finite loop integral over the k insertion Lagrangian points plus twofold time integrals. And for the standard approach, you need to do a k+3 body real phase space integral plus virtual loop integrals. And in these in separate pieces, you would encounter IR divergences. This means that these real and virtual integrals need to be regulated in D equals, regularized in D equals 4-2 epsilon dimension. So one of the major difficulty in doing this calculation is that for the higher loop order calculation, you need to do a multi-body phase space integration over a constrained phase space given by the measurement function. And this calculation is very difficult to optimize. And also you would encounter the bottleneck of doing D-dimensional integral reductions for a system of a large system of integrals. However, in our approach, all the integrals are manifestly finite, and the procedure that we described in my talk can be repeated at higher loop order, and the expressions for the building block for the Feynman diagrams can be recycled. This gives us a major advantage that is a systematic procedure which can be carried out at high loop order. And there's also hope that the novel method developed for computing finite integrals can be applied here. So in conclusion, we developed a new and efficient approach for systematic computation of event shape and especially energy-energy correlations at high loop order. The further development of our method includes applying this approach to high loop order and generalize to other type of observables. So in this approach tells us, allow us to study the nature of event shapes in terms of energy flow operators. And indeed, we find that once the event shape can admit the representation in terms of correlation functions, analytic study and precision study is more achievable. And this motivates us to perform a goal-driven study from both the theory side and experimental side to construct a new event shape observables that fulfill these requirements. And this opens doors to a new direction of the study of event shapes at Hadron Colliders. Thank you very much. This concludes my talk. Is there any questions?
Yeah, thank you very much for the nice talk. Questions? I have one question. In the calculation, in the one loop calculation, you said that there were bubbles which showed up to version integrals and they canceled in the end.
Sorry, I did not hear your question.
Is there any way how to? So you said that in the one loop calculation, they were bubbles,
yeah.
UV divergent bubbles, which then canceled the UV divergences. Is there any way how to rewrite the result in a way which makes manifest the UV finiteness?
So the integrals that we consider is UV finite, at least at one loop. The reason why we see bubbles is when we do the IBP reduction, these finite integrals are kind of decomposed onto a set of divergent master integrals. It's kind of because of the choice, arbitrariness in the choice of master integrals. Individual pieces might be divergent, but we know that in the end, when we combine things together, the divergence must cancel.
Okay, thank you. Yeah. Okay, if there are no more questions, thanks, speaker again. And we move to the next talk. So,
hi,
Carol.
Do you hear me?
Yes. Can you share your slides?
I try. Is it okay like this?
Yeah, excellent. So the next speaker is Karol Kamp from Charles University in Prague, and you will talk about soft theorems in multi-flavor Galilean theories. Please.
Thank you. Good morning and greetings from Prague. So as you already heard, the title is on soft theorems in multi-flavor Galilean theories. Also, as already pointed out by Johannes, it's a more general audience. So I will mainly focus on the first part on soft theorems with some more general introductory. Do you see down of my slide? Because I see the green is going a little bit, it's cut it.
We see it well. I see it well.
So, okay, so it seems that it doesn't correspond the green rectangles to what is what's supposed to be my whole page. So I would like to apologize that I will not talk in details about multi-flavor Galilean theories because it's rather technical, and I will prefer to focus on introductory. And of course, I will say a few words about Galileans, but not as I planned. As we all know, to understand basic structure of elementary particle, we use scattering experiments, and as we all learned, the main tool via quantum field theory is something we call scattering amplitude. And also, as we all know, this can be systematically calculated or in principle calculated using so-called Feynman diagrams. As an example, it's traditionally gluon amplitudes. It's also for the historical reason, as I will try to show in the following slides. So let me show or demonstrate how this calculation of Feynman diagrams can be difficult. Even if we simplify the problem of scattering n gluon to pure gluonic interaction at tree level, we will immediately see there are many diagrams to sum if we want to, for example, calculate 8.3 level. So if I count those diagrams correctly, there are, of course, we know there is 3-line vertex and 4-line vertex. So those vertices can combine to such a topologies. So, for example, if you focus on this topology with 4-point vertex on the left, right, and in the middle, there are 280 diagrams. And if you then focus on diagrams where are also 3-line vertices, for example, topology like this, there are even more diagrams, and it's even not the whole story. And if I, as I said, if I calculated correctly this 8-point example, there are 34,000 diagrams to sum. So we see that this problem is already complicated at tree-level diagrams, and it could be, I chose this 8-point, but we will see that it's already complicated for even lower number of diagrams. For 3-point, it's not such a problem. It's only one diagram, and on shell is 0. For 4-point, this is a standard exercise, and one can easily calculate by hand those diagrams. And even though it's not a short calculation, the final differential cross section looks nice. For the 5-point, it's starting to be more complicated. So I draw those two topologies wanted to deal with. Total number of diagrams is mentioned here. Of course, we are capable to write down what it could be, even though we would be probably lazy to write down all 25 diagrams. It would be some mixture of terms with Sij and polarization vector. Of course, we can expect this double propagator and this single propagator. So it looks simple in the Feynman diagram picture, but on the paper to sum all those diagrams is really complicated. So it was possible to do this 5-point calculation, but 6-point calculation seemed impossible by standard method. But there was a motivation to go further. As we know, there was a intention to build LHC-like experiment in US, so-called superconducting super collider, which was approved in '83, motivated this work written by Park and Taylor. And just so you can believe me that they were really discussing this 6-gluon calculation. So I will read it for you. Also, some individual contribution to 4-jet production have already been analyzed. The 2-gluon to 4-gluon scattering, which is the dominant contribution for a wide range of subprocess energy, has remained beyond the scope of previous computational techniques. So this is basically what I stated in the previous slide, that it's impossible to calculate this 2 to 4 gluons, it means 6 gluon scattering using the standard method. So they have to make use of the different techniques. It's stated at the bottom of the page, if you can see it, which is the method to use the application of extended supersymmetry. But I'm not going in details what these methods, what those methods are. What is interesting is the conclusion in their paper, which proved that they already seen some pattern, and this pattern can be summarized in the following conjecture for the so-called maximally helicity violating combination of gluon. Of course, the amplitude depends on the combination of helicities of the outgoing gluons, expressed via the polarization vector. But if you are interested in certain combination, there is so-called maximally helicity violating combination, which is the first non-zero combination for the, as stated by the name, maximally helicity combination. But what is very interesting, that the result is simple. It's I mean, I summarize what means these brackets, but it's not important. Important is the lecture. Even though, as I said, for example, for the 6, it would be two gluons with the opposite helicity as the other 4. Even though it wouldn't be very easy to calculate, as I said, conventional method, still after thousands of pages of calculations, you will end up with a very simple result. Of course, the supersymmetry can help you to reduce number of combination, but still it's a complicated calculation. So natural question can arise if there is some better way how to calculate how to sum these Feynman diagrams. So I will go through via some way how to do it, which ends up with so-called BCFW. First important step is so-called color ordering. We can strip amplitude. We can separate the group structure, which is hidden in these T generators. In this case, SU3 for the gluons. And then we can deal with ordered amplitude, and as it is clear, all possible combinations in the usual calculation is now reduced to ordered to the combination which are ordered cyclically ordered. So this immediately helps you considerably. For example, if you look on the possible poles, we are still, once again, I have to stress, we are still calculating only 3-level diagrams. So thanks to the ordering, the only possible poles are consecutive momenta. So if we start with I, there should be the sum, and end with J, there should be this pole, the only possible pole. Another ingredient is, which seems very easy, if you have all this bunch of Feynman diagrams, and if it is allowed by helicity conservations, it is clear that so if such a two subdiagrams, which we call ML and MR, are possible, so it's natural if we, as we say, if we sit on this pole, on this factorization channel, then from all those diagrams, this is the only contribution which survives. And then the amplitude, or this limit, when we sit on the factorization channel, is the sum of this left and the right part, and of course between is this is the propagator. And this was the so first important step is possible to strip the amplitude. Next step is this as we call Weinberg's theorem of one particle unitarity, and the last very important ingredient in the something which is nowadays called BCFW is possibility to go to complex plane by the following trick. We can shift two external momenta by adding another for the moment unspecified momentum q multiplied by complex parameter z, and as we want momenta conservation to be still true, we edit it in the one momenta, we have to subtract from the other one. And on top of that, we want to keep Pi and Pj on shell. So in this case, these are gluons, we want them massless. So this gives us another relation on those Q. So Q is not completely random, but should fulfill this these constraints. In any case, amplitude, which is a function of momenta, now becomes a meromorphic function of z parameter. Meromorphic, it means we expect some poles, but these are well-defined poles coming from propagators. And trivially, if we put z equals 0, we are back to the original function. Here I just write down the usual Cauchy theorem. It's a trivial Cauchy theorem as we know it from introductory courses of algebra analysis, mathematical analysis. What is now important assumption, and I will discuss this in deep in the following slides. We have to assume that amplitude vanishes for z going to infinity. This enables to relate original function, original amplitude, which is a for z equals 0, with its residues, with some of the residues. As I said, those poles came from propagators, so we have to focus on solution of when the poles is equal to 0, when the function has the poles, so we can sum those so residue. It's a simple algebra. What is important to realize, because as I said, we shifted exactly two momenta, I and j, for example, 1 or 2. It's up to you to decide at the beginning which momenta you want to shift. But if we are looking for the solution, when this has a solution in the complex plane, it's clear that among those A to B, the P so the momenta are PA to PB, it's clear that exactly one and only one, those shifted I and J can be inside, because as I stressed, we subtract in the J this ZQ, so there wouldn't be any Z if both of them are there, and of course none of them, then it's clear. So exactly one shifted momenta could be between A and B, between PA and PB, and then we have simple equation to solve. After simple algebra, we can write what is it, and because these are the simple poles, as we know from this one particle unitarity, then the residue are very easy to calculate, and the result is written here. if I go back, just a reminder, what is the original amplitude? So now we know what is this residuum. So we can plug it back and we know what is the amplitude. So summary, it's based on two-line shift. It's a recursive formula because those left and right amplitude, they have less number of legs than the original amplitude. What is important that if we compare it with the usual Feynman diagram calculation, the number of terms is much smaller. And what is also important for us for our discussion is that all ingredients are on shell. For the theories I want to discuss here, it's important to return back to the assumption we made at the beginning of this PRUR of this BCFW, and it was that amplitude vanishes for z going to infinity. If not, it's clear we have to somehow add further information to Cauchy theorem. And this will be very important in studying effective field theory, which is the subject of this talk. Schematically, we want to study for the simple scalar field, effective field theory. We have some infinite sum of terms in the language of Lagrangian, schematically written as some derivatives acting on scalar field phi. So there will be 4 phi's, there will be 6 phi's, and so on. So it's just the schematical example how typical effective field theory can look. I put it here just to stress what we are looking for. So we have a Feynman diagram with 4-point vertices, which comes from this second term, and then we have this contact term. In the language of amplitude, it's written here. Of course, we are looking for some relation how to connect these two terms. As we know, homogeneity allows to combine these two terms. Power counting helps us to combine these two terms, and we want to know how to link these two terms. So this is the work which we done in several papers done in collaboration with Clifford Cheng, Jiří Novotný, Josh Shen, Jaroslav, and Kong Gao. So I will try to be brief because I spent a lot of time on this introductory. So if we really want to build it from the most simple example, let us focus on what this most simple example is. So it's definitely not 3-point amplitude, as there is the amplitude is 0. It's 0 for the effective theories with derivative couplings. So the only non-zero theory would be 5-cube theory. So it doesn't look like a typical example for the scalar effective field theory. So we have to focus on 4-point scattering, and I already show you this combination of diagrams. We can easily convince ourselves that the most simple example is with 2 derivatives. So let us write down the example with 2 derivatives. However, it can look very complicated diagrams, but it always represents a free theory which can be proved very easily by this field, by using this F-phi and by other field redefinition. So let me summarize outcomes so far. Then for the non-trivial simplest case, it has to have more than 2 derivatives, or it has to have more flavors. So let me start with the example with more flavors, and this is how we also started this task with Jaroslav and Jiří a few years ago. It's very complicated generally. And we have to assume some simplification, which will be given by a group structure. Similarly, as in the gluon case, we will assume some flavor ordering. Then the number of diagrams is smaller. Still, you have to make the crucial assumption between this blue constants and this, so between this propagator function and this contact terms. Natural example is so-called soft limit. So we can assume, so we can say something about this, something on the relation between 4-point vertex and 6-point vertex is natural candidate. How to combine them is so-called soft limit. Of course, this was not invented by us, but this is well-known fact which is connected with the name Adler, and it is studied in the literature for many decades. What we want to present is so-called bottom-up construction. So we would need two parameters, sigma, which will count somehow the softness of the amplitude, how it goes to zero. If one momenta is going to zero, how fast is the whole amplitude going to zero? And naturally, as I already showed you, very important parameter is so-called is the number of derivative. So it depends, of course, on number of legs in vertices. So we found out this so-called parameter rho very important in our analysis, which somehow average number of derivatives. What is important is this table. Of course, more derivatives, easier the soft limit can be. So for us, very important is to study non-trivial cases, and this table summarizes the non-trivial cases. So given the number of derivatives, what soft limit should at least be so it is interesting or non-trivial. So I already mentioned this rho equals 0, so two derivatives. We proved that there is only one possible theory, so-called nonlinear sigma model. Another case will be more interesting. It's rho equal 1 and sigma equal 2, so it's double soft limit. Number of derivatives you see is bigger, and it's correspond to number of fields. So for every field we have always one derivative. So we can focus. We know what we are looking for. We want this Lagrangian or this amplitude has soft limit. This double soft limit, it will somehow shift. It will fix the parameters in front of those vertices. We can find the symmetry which is responsible for this condition, at least for these two terms. And we can ansatz, or we can demand it for the whole Lagrangian, not only for 4-point and 6-point vertices. And we can solve this recurrent relation. And it's possible to do it. The solution is square root, or to better state it, it's so-called already known theory, Dirac-Bohr-Infeld, or DBI for short. So it was known theory, but what I wanted to convince you that this bottom-up construction is really possible to prove without any doubt that this is the only theory with these properties. We can continue and finally get to example Galilean. It's rho equal 2 and double soft limit. So number derivatives rise a little bit. And again, the similar construction, we find out that this is the only theory. We can also find out the responsible symmetry and find this theory. what was, again, the theory was known when we opened this bottom-up construction. However, what was not known was this enhanced soft limit. Again, for rho equal to, we can ask if it is possible to increase the softness of the amplitude. In principle, it's possible because this Galilean Lagrangian, it has several parameters. So we can ask, is it possible to find some combination of those parameters so the amplitude behaves even better than double soft limit, and it has this triple soft limit, the answer was that yes, and we publish it in this paper. However, we were not capable to prove it up to all orders, but very soon after, just 1 month after our article, Kurt Hinterbichler and Joyce publish or explain us what is the hidden symmetry responsible for this behavior. So this can continue, and we can use it for the whole classification of effective field theories, which we summarize in this paper. So in the last transparencies, let me focus what I promise on this multi-flavor Galilean, but it will be very brief. Of course, now we discuss only scalar, single scalar with the expectation of cyclic ordering for multi-flavor for this nonlinear sigma model. And we can ask what we can do next. So there are different directions one can take. You will hear in the after coffee break about possibility of possibility of mixing spins. We can go, of course, in the case of nonlinear sigma model, to higher orders, and we can, of course, discuss a little bit deeper multiple flavors. So back to the Galileans, why they are so important. As I didn't mention, they are important, for example, for general relativity in GR, more specifically in the modification of general relativity. We need to fulfill so-called measurement at solar system scales. So there should be, in the whatever we do with general relativity, in some sense, it should agree with the measurement. So we need something which can be called a screening mechanism. And one of these mechanisms is Weinstein mechanism, which is connected with the theories with second derivative of equation of motion. And this is exactly the Galilean theories. If you calculate it from the amplitude point of view, you can calculate 3-point, 4-point amplitude, 5-point amplitude. What we notice, or what can be easily noticed, that of course 3-point should be 0, as we already mentioned. But for the 4-point and 5-point, you can expect some complicated propagator structure. What we found out that the amplitude is relatively easy. The response reason for this is so-called Galilean duality, and it is well understood for the single Galilean. If you look at the Feynman diagrams, it's clear it's connected with 3-point vertices. So if 3 points can be somehow, if we can get rid of it from the theory, of course, or these propagator diagrams are 0, and we have only the contact terms, which is exactly what we are getting for the result. It looks like the contact term. So it plays an important role, these dualities, and this was our main motivation why we decided to look deeper on these multi-Galilean theories. So it's a work in progress, and as I said, it will be rather technical to go into the details, and hopefully we will soon summarize this in the article. But there is an important discussion. Whatever we present in this article, it should contain this discussion on dualities, because this is crucial point in the single Galois case, and it must be important also in whatever this multi-Galois theories is. It should tell you what is the role of three line vertices. And with this is connected so-called new soft theorem. It's a soft theorem without zero on the right-hand side, roughly speaking. And it should be also connected with the definition of Galois theory. As I show you, this bottom-up method is equivalent to this requirement of the second order equation of motion, but one should check whether this is still equivalent also for these multi-Galois theories. And of course, one can add some classification which is still missing completely. There are some articles which try to classify it, but complete classifications is still missing for these multi-Galois theories. So thank you very much, and I hope I didn't go off the time. Thank you very much.
Okay, thank you. Any questions for Karol? Well, I don't see any questions. So thanks, Karol,
Thank you.
again. And we will have now 10-minute break, and we will reconvene at 9:45. Okay, so we continue our session. So next speaker is Philip Trochil. Can you please share the slides?
Can you hear me?
Yes.
Okay. Does it work?
Yes, and Philip will talk about scalar vector effective field theories from sublimits. Please start.
Okay, good morning. I thank the organizers for being able to speak here. It is a pleasure. So my contribution is about a recent work with Karol Kamp, Jiří Novotný, and Jaroslav Trnka. There will be some overlaps with the previous talk, and currently it is still work in progress. So the title is Scalar Vector EFTs from Sublimits. Basically, we want to find a unique theory fixed by its soft limits, which contains photon and special gluon, which is massless scalar, as you have heard. So some introduction, we also heard this already. So in 1986, Park and Taylor calculated 6.3 level gluon amplitudes, and the result was very simple. So the motivation of this modern amplitude method is to find better ways to calculate amplitudes than the traditional Lagrangian approach. Also, the mapping from Lagrangian to amplitude is many to one, so you can have a lot of different Lagrangians which correspond to one same theory. Also, new variables may uncover previously hidden structures, as is in the case of the amplitude hedron. And of course, the final goal is to reformulate QFT without Lagrangians. So part one will be about the bootstrap method or bottom-up construction, as we have heard from the previous talk. For that, we need some key amplitude properties, and they should be Lorentz invariance, locality, and unitarity. Some amplitudes, of course, can have some additional properties like gauge invariance, supersymmetry, or in our case, subbehavior or enhanced subbehavior. So the basic idea of this bootstrap method is basically invert this picture of which corresponds to factorization. So if we can split some bigger tree amplitudes to some smaller sub-amplitudes, we can also glue some smaller tree amplitudes to some bigger amplitude. And of course, we have to add some contact terms which we can't get from this factorization condition. So the contact terms are this 6-point star shape thing. Also, I will skip over this slide because we already heard about this rho parameter. It basically averages the number of derivatives. Here are some examples of theories which are single rho. So all its amplitudes or tree amplitudes are described by the same rho. So we have rho equals 2. This is the case of Galileans, rho equals 1. Here we have Dirac-Born-Infeld, which is a scalar theory, and Born-Infeld, which is a spin 1 theory. And for rho equals 0, we have nonlinear sigma model and, of course, free theory. So one key thing we need to know is the contact amplitudes, how to construct them for massless particles at least. So we have some of our system of simple rules. The amplitude should be polynomial in spinor brackets of external momenta. The power counting sets the amplitude mass dimension. So if we know the rho, we can calculate the mass dimension of this amplitude if we know the number of legs. For example, for dBi or Bi, because rho is equals 1, the mass dimension is equal to the number of legs of the dBi or Bi amplitude. And the last thing is the amplitude should obey or have the correct little group scaling. So if we scale some particle with helicity h, we should see some corresponding scaling of the whole amplitude. So our actual problem is there a unique theory with Galilean-like Weber counting, so rho equals 2, containing special Galilean coupled to photon? And this question was first raised in this paper by Henriette Elwang in 2018. And of course, assuming helicity conservation, there are 3 4-point seed amplitudes. So we have purely scalar amplitude, an amplitude with 2 scalars and 2 photons, and 4-photon amplitude. By helicity conservation, of course, I mean the number of plus photons is the same as number of minus photons. And by applying the rules from this slide, we actually get some expressions for these 3 4-point C amplitudes. And then we can start gluing them together. So for example, how to get the amplitude A24. So that means it's a 6-point amplitude, and 2 means 2 photons and 4 scalars. So there are 2 possible ways how to use these seed amplitudes. We can make one diagram, or where we glue this 4 scalar the amplitude with this 2 scalar amplitude, or we use 2 scalar amplitudes. And of course, we have to add some contact term, which in this case is it contains 29 different structures or terms. And for the case of this A24, if we demand OT cubed subbehavior for any Galilean leg, we get a system of equations, and we are actually able to calculate all these 29 constants. So actually we have 29 6-point constants, and then 1-point constant for each, 1 constant for each 4-point amplitude we used. And we use 2. We use the 4 scalar and 2 scalar. So there's 39 constants in together. And by demanding this OT cube subbehavior, we are able to calculate 30 of them. So 1 constant remains unfixed, and that is the overall normalization of the amplitude. For the case of the amplitude A42, where we have 4 photons and 2 scalars, there is actually 3 diagrams we can with 1 propagator, and then there is also the contact term, which in this case is 42 terms. And for the case of this A42, demanding this special Galilean subbehavior is not enough. We can only fix some of these 42 constants. But this can be saved by demanding a special sublimit where we make all the photons with the same helicity soft simultaneously. We call this the multi-chiral limit, and it was first explored in this for the case of Born-Infeld in this paper by Chong, Kamp, Novotny, Shen, Trankanen. So by demanding both this OT cube subbehavior for any Galilean leg and OT subbehavior for all the plus photons or all the minus photons, we can actually fix all these 42 constants in the 6-point contact terms, and also one of the 4-point constant. So one again remains unfixed, and it corresponds to the overall normalization. For A60, so that's an amplitude with 6 photons and 0 scalars. We actually need, we can always also use the multi-chiral limit, but we need a stronger one. We need O2 squared. OT is not sufficient. And for A06, this is a purely Galilean amplitude, and it was studied in these papers, older papers from 2014, 2015. What about 8-point amplitudes? This is where it gets a lot harder. The amplitude A26, so 2 photons, 6 scalars, is fixed completely using the Galilean soft limit, and it contains 696 8-point constants. the amplitude, yes, and I was able to actually to verify this. For the case of the amplitude A44, there is 2,152 8-point constants, and a Galilean soft limit should be enough, but currently we are in the process of verifying because there are some problems, but it should be enough. For the case of A62, so 6 photons, 2 scalars, it shouldn't be enough, and it seems it's not enough. So we need some additional possible limit, but we do not know currently. And there is 1,280 8-point constants. And for A80, this is the purely photon case. There are 94 8-point constants, and so far we also have no idea how to fix this one. So this is like summarization picture. So at the top we have the seed amplitudes, 4-point seed amplitudes. There are 3 of them. Second row is the 6-point amplitudes, then 8-point amplitudes, and the last row is 10-point amplitudes. Of course, we are probably won't be able to calculate them using this method. Of course, I should explain the colors. Sorry. I should also explain the colors. Zero residue at infinity demands a naive condition. This is an analogy from BCFW, it basically says that a number of photons should be lesser than number of scalars plus 2. So those are the green amplitudes. So for example, A44, 4 is lesser than 6, so it's a green, but A62, 6 is not lesser than 4. And these green amplitudes should be reconstructible if we know the previous row. So you can actually see what amplitudes you need if you go if you backtrack these arrows. So for example, for A44, you will need A24 contact terms and A42 contact terms, and then also of course A04, A22, and A40. Okay, so this is the first part about the bootstrap method, and the second part, Lagrangian method or Lagrangian approach. So as we already heard, Galileans comes from the origin is the decoupling limit of Hornetsky theories, which is the hyperscalar tensor gravity theories. Of course, there are exceptionally FTs. We've already seen this Lagrangian, and this is the Lagrangian of the general Galilean in d dimensions. If we want to get the special Galilean Lagrangian, we just plug these special values for these dn's. We have all Galileans have this Galilean symmetry. It's a shift symmetry, and special Galilean also have this has this hidden symmetry, which was explained by this paper by Kurt Hinterbichler. So the former, the shift symmetry ensures OT squared subbehavior. The hidden symmetry actually ensures even stronger enhanced OT cube behavior. And we also know that these symmetry properties carry over to one loop amplitudes for the case of the special Galilean, which we did in this paper in September. Special Galilean can be described geometrically as the fluctuations of a d-dimensional brane in a 2D-dimensional flat space. So we have some metric on this brane, which is actually functional of the phi, which is the Galilean field. Another interesting object is this external curvature tensor, which is, as you can see, a triple derivative of phi. Alpha is some scale, and from the Gauss equation, we also get the formula for the Riemann tensor. This comes from the fact that the two-dimensional space, the embedding space, is flat. Then we can also define these invariant measures, and this special sigma invariant, which is basically a ratio of these two invariant measures. And there is a claim that any Lagrangian constructed using these presented building blocks is automatically invariant under the special Galois-Hidden symmetry. So we get this property for free if we use these building blocks. And if you want to add photons to the story, this special Galois-Hidden symmetry can be implemented in this way on the photons. Okay, so knowing these building blocks, we can try to construct some Lagrangian. Of course, the most simple one is the two-photon Lagrangian. It looks like this. So we have two Fs contracted with the inverse metric tensor and some potential V, which is a function of this sigma invariant, and then there is a determinant of the metric. This Lagrangian is actually a bit more general than the Lagrangian that appeared in this paper, also by Kurt Hinterbichler in November. For example, this Lagrangian can generate helicity violating amplitudes if the derivative of this potential V at zero is not zero. And then, of course, we can construct some non-minimal Lagrangians, which contain 4 photons or 6 photons or more photons. For 4-photon Lagrangians, there are many possibilities. We can, for example, use 4 Fs and 2 external curvatures. There's actually 12 different contractions. Or we can use covariant derivative of F squared times 2 Fs, or 4 Fs and covariant derivative of the external curvature, and so on. For example, if we look at the A42 amplitude calculated from this Lagrangian or Lagrangians, minimal Lagrangian, the photon one, the first one, itself cannot produce the correct amplitude I42 that we found in the bootstrap using the bootstrap, because it won't have the multi-chiral limit. But we can add L1, the first one, from the non-minimal Lagrangians, and this can help. This will actually restore the multi-chiral limit. Then adding L2 with df squared f squared actually won't change for this amplitude anything, because it only generates structures that are already present. So it will only shift some constants that comes from these potentials. I forgot to mention that these potential V's can be different for any can be a different function for any for all the possible contractions of these building blocks. So we have quite a lot of these potentials actually, even in the case of 4 photons. And these remaining 2 Lagrangians, L3 and L4, at least for this amplitude A42, will not contribute. Okay, so to summarize the first part, the bootstrap one, of course, we have 2 approaches, the bootstrap or Potomac construction, and then the Lagrangian approach. because the number of contact amplitudes grows very harshly. We are already at hundreds or thousands at endpoint. We'll probably be in maybe millions at 10 point. We cannot go too far with the bootstrap method. On the other hand, as I mentioned in the first slide, the bootstrap method has no redundancies typical for Lagrangian approaches. So we are calculating directly the amplitude. So that's it. From the bootstrap method, it seems that this subtheory that possesses both the multi-chiral limit and the soft Galois soft limit, it might exist, but so far we haven't been able to find a corresponding Lagrangian. One important point is that the bootstrap method only gives a hint of existence, not a proof of existence. And of course, its usefulness is that it can exclude some theories from existence. And to summarize the part 2 about the Lagrangian approach, at this point we have an infinite amount of theories that automatically have this OT cube special Galois behavior, and they are parameterized by possible structures built from these building blocks, and the corresponding potential V in this box represents the chosen combination of building blocks we used. So our task is to try using the constraint obtained from this bootstrap method to reduce this set of this infinite set of possible Lagrangian. And we know that this multi-chiral limit reduces this set a lot, but we haven't found the unique theory yet, if it exists. And of course, it would be nice to find some additional properties other than this multi-chiral limit that could help to restrict the set of possible Lagrangians even more. And our outlook is, of course, make some conclusion, or maybe say that this theory probably doesn't exist, or find some properties which will enable us to fix it, to make it unique. Okay, so that's all. Thank you.
Thank you very much. Any questions? I don't see any questions, so thanks again, and we will proceed to the next talk.
Thank you.
Thank you. So the next talk is by Dr. Saurabh Gupta. Can you please share your slides?
Is it visible?
Yes.
Is it full screen now? Huh?
Yes, yes. Okay, great. So the next talk is by Saurabh Gupta, and he will talk about coupled n equals 2 supersymmetric quantum systems, symmetrines, and supervariable approach. Please start.
Thank you. Let me start with thanking the organizers for giving me this opportunity to present my work, and also thanks to the chairperson of this session for allowing me to present my work in this conference. So I'm going to talk about the symmetries existing in the coupled n is equal to 2 supersymmetric quantum mechanical systems, and their possible connections with the operators of differential geometry. And in the later part of the talk, I will little bit briefly go about how these symmetries, which is existing in the n is equal to 2 supersymmetric quantum systems, can be derived using supervariable approach. So this talk is actually based on the work done in the collaboration with this, my students, Aditi, Anjali, Binu, and it's got accepted recently for publications, and there's a link for archive also there. So here is the outline of my talk. I will start with the introducing n is equal to 2 supersymmetric quantum mechanical model. I will briefly talk about what is the symmetry existing in this n is equal to 2 supersymmetric quantum model, and what are the key properties of any general n is equal to 2 SUSY quantum mechanical model. And then it comes to the motivation for our present work, which is primarily motivated by a conjecture. It says, I will introduce the conjecture later in the talk, and we will try to give a proof of that conjecture with the help of 2 different examples. And then we will consider a generalized superpotential, and generalized superpotential is actually contains the superposition of different potentials, and we'll discuss what are the symmetries existing in the case when you take a superposition of different potentials. And then we will move to the super variable approach, chiral and t-chiral super variable approach, and we derive the on-shell symmetries, on-shell nilpotent symmetries in the generalized case. And finally, the invariance of the Lagrangian we are going to prove with the help of super variable approach, and we provide the geometrical interpretation of the invariance. Yeah. And finally, we summarize. So let me start with the super variable approach to the description of n is equal to 2 supersymmetric quantum model. So we begin with the n is equal to 2 super variable x on a 1,2 dimensional super manifold. See, the 1,2 is which is parameterized by 2 Grassmannian variables theta and theta bar apart from the usual ordinary variable t here, which is turns out to be evolution parameter if you see later on. And this super variable we can expand along this Grassmannian direction like this, where this q psi bar, they are the basic dynamical variables, and e is the auxiliary variable. Here psi bar are fermionic, and q and a are the bosonic variables. And all these variables are the function of the evolution parameter t. We can define now the 2 supercharges q and q bar in this fashion, and this partial derivative del by del t, del by del theta, and del by del theta bar, actually they are later turns out to be the generator of the translation along t, theta, and theta bar directions. So the SUSY transformation on any this super variable x, we can write with the help of these 2 supercharges q and q bar in this fashion. So the generalized Lagrangian for n is equal to 2 SUSY quantum mechanical model in 1,2 dimensional super manifold, we can write with the help of super covariant derivative d and d bar. I will define like this here, super covariant derivatives, and this w is the superpotential. It is an arbitrary function of this x, which depends on theta and theta bar. So this is the general Lagrangian for n is equal to 2 SUSY quantum mechanical model, and this Lagrangian have now this superpotential, what w is over here, we can expand it. It's actually a function of arbitrary function of x, and it can be expanded by the Taylor expansion around the ordinary variable q. And in this expansion we will have only few terms, only up to w prime square, because up to w double prime. Sorry, up to w double prime we will have a term, because all the other term will be 0 because of the Grassmannian nature of this theta and theta bar. And if you do the proper Grassmann integration, and so modulo total derivative, we can write our Lagrangian in this form. Here A is auxiliary variable, q, psi, and psi bar are the basic dynamical variable, and the prime is the q derivative with respect to q, and double prime is double derivative. This Lagrangian actually have two sets of off-shell nilpotent fermionic symmetries that is listed here. This is one set of fermionic off-shell symmetries. Another set of symmetries is here. These are nilpotent symmetries, means if you apply twice S1 on here, S1 square is 0, and if S2 square is also 0. These are off-shell nilpotent. Off-shell nilpotent is not going to use the equation of motion. That's why it's off-shell nilpotent. These are continuous symmetries, of course, and this is a fermionic in nature. And under these symmetries, the Lagrangian remains quasi-invariant, as you can see it from here, that it goes to a total derivative in both the cases. Apart from these two fermionic symmetries, we can construct a bosonic symmetry in the theory in this following fashion. Means if you take the anti-commutator of these two symmetries S1 and S2, and it gives you a bosonic symmetry of the theory S omega. And under this symmetry, bosonic symmetry, is also your Lagrangian goes to a total derivative of itself, d by dt of L. And since we have three different continuous symmetries in our theory, two fermionic and one bosonic, so we can have can construct the Noether conserved charges with the help of these three symmetries. And these charges are here, Q bar corresponding to S1 and S2, and Q omega, you can see that it's nothing but the Hamiltonian of the system. This can be identified as the Hamiltonian of the system. It's charges corresponding to the bosonic symmetry. Apart from this continuous bosonic and fermionic symmetry, we also have a discrete symmetry in the theory. Actually, I have written this physically quote unquote. I will explain what is in the later part of the talk. What is physically I mean to say. There exist several discrete symmetries, but the relevant one is what they have pointed out is this one, discrete symmetries. And the algebra of the three continuous and one discrete symmetries are listed here. So you can see this algebra: S square is 0, S2 square is 0, anti-commutator of this S1 and S2 constructed as omega, and it commutes with S1 and S2. And you can see that S1 and S2 are related with this star operation. Star is nothing but the discrete symmetry operation. So this plus minus sign, it's dictated by two successive operations or discrete symmetry operations on any generic variable phi of the theory. If star of phi turns to plus, then we have to take a plus sign, else the minus. And this actually, this is algebra is the same, the algebraic structure of these symmetries as the same as the algebra obeyed by the DRAM cohomological operators of differential geometry. So on a compact manifold without any boundary, there exist three differential geometrical operators or DRAM cohomological operators: d delta and capital delta, exterior derivative, co-exterior derivative, and the Laplacian operator. So it is a reminiscent of the algebra that is obeyed by DRAM cohomological operators. We can find a connection one-to-one with the symmetries to the DRAM cohomological operators here. So the motivation of my work comes from here. There is a conjecture. One of the main motivations is there to prove the conjecture posed by Malik and collaborators in this paper 13. So as the conjecture says that there might exist more than one set of discrete symmetry transformation which provide an analog of the Hodge duality operator of differential geometry. And the more motivations come that we also want to study for a general case of superposition of superpotentials. We take some polynomial type of superpotentials and superimpose few of them, and we want to see whatever the symmetries existing in that case are the same kind of algebraic structure as the algebraic structure here appears in the case of superposition or not. If yes, then what is the difference or what is the similarities? Finally, the anti-chiral supervaluable approach, those symmetries which we have derived, we should want to have a geometrical backing for them. So we have looked for the anti-chiral supervariable approach to derive all those on-shell symmetries. Here we are going to deriving the on-shell. Earlier, those symmetries mentioned was the off-shell symmetries. Here we have focused on the on-cell. So we start with the we take a generalized superpotential of the form in this form W prime. Here this A and B are the integers. It could be positive, could be negative as well, but we have to take in an appropriate order. What does it mean by taking in appropriate order? It means that A are going from A to B is equal to A plus N, which N being a positive integer. And the beta j's are the coefficients, constant coefficients are here. Now, suppose if I choose A is equal to -1 and B is equal to 1, this gives a very simple one. W prime is this potential given like this one. This is already this potential is listed here in this paper in GNPA long back at 87. This kind of potential has been studied earlier. Now, the interesting thing is that if you look at this potential W prime, and if I put the lambda is equal to 0, whatever we left out with is it's the superposition of harmonic oscillator plus free particle potential. Suppose if I take mu is to be 0, what is left out will be the harmonic oscillator plus a Coulomb like 1 by q type of potential, superpotential. So this our choice of the generalized W prime actually is the superposition of different kind of superpotentials. Taking the values from A and B, we can generate a whole lot of geometrical series of superpotentials which is superimposed with each other. So we took this generalized superpotential case, and with that superpotential, our Lagrangian looks like something this. And we look for the symmetries. What could these symmetries this Lagrangian could have? So we got these kind of symmetries, S1 and S2, two set of symmetries. As we are already expecting that we should have at least two fermionic symmetries, which are here S1 and S2. And naively, if I take the anti-commutator of these two symmetries as the earlier have done, we have end up with a bosonic symmetry. And these are this over here. And under all these symmetries, two fermionic and one bosonic, my Lagrangian remains quasi-Eulerian as it goes to a total derivative. And apart from these continuous symmetries, we had derived also the charges and currents. So I am not presenting over here. The Lagrangian further have 8 sets of discrete symmetry transformations. Apart from those 8 different sets of discrete symmetry transformation, we found that only 2 sets are physically relevant. Now let me tell you what the physically relevant I mean to say it here, which means that which can provide the analog of the Hodge duality operator. I mean, these 2 sets, rather the other 6 sets of the discrete symmetry transformation, they don't provide the analog of the Hodge duality operator. Only these 2 sets which is listed here can provide the analog for Hodge duality operator. What I mean to say, let me very briefly give about the DRAM cohomological operators and what I am trying to say it here, if I able to convince. DRAM cohomological operators, this is algebra of DRAM cohomological operators. Exterior derivative, D, delta co-exterior derivative, and capital delta Laplacian operator. So D square, delta square, both are 0. Delta capital is the anti-commutator of D and delta, and it commutes with both of them. And you can have co-exterior derivative related with the exterior derivative with this star. With this star is the Hodge duality operator. The co-exterior derivative and exterior derivative are related with the Hodge duality operator. And this plus minus sign is dependent upon the dimensionality and the form of the object which we have taken the. Interestingly, we have also in the case of superimposition of the superpotential, the same algebra as the algebra of DRAM cohomological operator. And this relation, which relates, suppose I am trying to map S1 with delta, delta with the S2. So, and DRAM cohomological operators satisfy this relation. So we must also have something which can relate the S1 and S2. And the role of star is played here by this discrete symmetry transformation. And this transformation as well as the inverse of this also hold. So this transformation plays a crucial role to get whatever the discrete symmetry transformation, we call it a physical. If apart from satisfying to this S1, S2, and S omega already satisfy this kind of algebra. But if S1 and S2 are related through this discrete symmetry transformation, those which satisfy this kind of relation, then we call it perfect symmetry, or we call it the physically relevant discrete symmetry transformation. And these are two in the numbers here. So essentially, we have proven the curvature by showing that not one, but we have at least two set of discrete symmetries which obey, which can be shown as the Hodge duality, mapped with the Hodge duality operator. Now, in the second half of the talk, let me briefly go about this anti-chiral supervariable approach. I will give a brief synopsis of this chiral and anti-chiral supervariable approach. So, in this supervariable approach, we start with the ordinary variable in the theory, and we generalize it to their anti-chiral supervariables on a supermanifold, which is parameterized by the two Grassmann variables theta and theta bar, apart from the usual bosonic coordinates. And then the second step, these supervariables, we expand it along the Grassmannian directions in terms of the secondary variables. Now, finally, we sought after about for the SUSY invariant restrictions. With the help of the SUSY invariant restrictions, we actually get a relationship between these basic variables and the secondary variables. And this actually approach is basically developed by Malik and collaborators in series of papers. One of them I have listed over here. So I will apply. I applied this kind of chiral and anti-chiral supervariable approach. So we start with the anti-chiral supervariable approach. In this case, the ordinary variables, the theory Q, psi, and psi bar, we generalize it to their corresponding supervariables on anti-chiral super submanifold. This only characterized by a single variable G bar here, theta bar here, where it's lambda is a fermionic secondary variable, omega and omega 2, or these are bosonic secondary variables. After generalizing it in the second step, we look for the SUSY invariant restrictions. So the SUSY invariant restriction, first we find that this is trivial one, and the second and third we sort after this second SUSY invariant restriction. If we apply this SUSY invariant restriction and put these anti-chiral supervariable expansions over here, so we immediately get the relationship between the primary and the secondary variables, bosonic primary and secondary variables of the theory in this session. But it still is not end of the story, because we have to still find the omega 2, because omega 1 and lambda is already been found by these conditions. Omega 2 is still missing, so we have to look for a more complicated kind of involved super SUSY invariant restrictions, which are denoted by epsilon t, is something like this big expression, and this if you general, and the capital gamma is the generalization of this epsilon on the anti-chiral super submanifold. And if you make this SUSY invariant restrictions over there, so you can get the value of omega 2. Now, putting all these values of secondary variables in the superfield expansion, we get the expression for the Q, psi, and psi bar in this fashion. You can see that the last part here, what is coefficient of theta bar here, it actually gives you what is the value of this symmetry transformation. So the and if you can see that if you take the translation along the Grassmannian direction, it is same as that what is the result you get after applying the S1 symmetry on the same variable. So in other words, we can say that if you take the translation generator del by del theta bar along this direction, it's same as that having the first symmetry S1 on the ordinary variable. So this is a super variable phi itself, ordinary variable. Now similar thing we can do on the we can do with the help of chiral super variable approach. The other fermionic symmetries S2, we can reduce it using chiral super submanifold, which is now characterized by the other Grassmann variable theta, and we can find out the SUSY invariant restrictions. We have not listed here, but we find out the SUSY invariant restriction, which gives the relations between the basic and secondary variables of the field. After getting those values, we can put it back in the expansion of super variables, and with the coefficients of the theta is nothing but the symmetry S2. And we can also identify in this case as well del by del theta. This translation along this theta direction is nothing but same as the symmetry S2 acting on the ordinary variable. And the final part of this talk will show the invariance of the Lagrangian. So we start the starting Lagrangian. I started with that we can generalize onto 1,1 dimensional anti-chiral super submanifold. So this is the generalization of the Lagrangian, the anti-chiral Lagrangian. This one superscript 1 is denote the generalization of those correspondingly ordinary variables on the anti-chiral directions, 2 on the chiral directions. So this is the generalization of the original Lagrangian along the anti-chiral direction. This is the generalization of a Lagrangian on the chiral direction. And we substitute the value of this Q and Q bar, we get a very nice cute big expression for this L tilde AC and L tilde of T along the chiral anti-chiral supermanifold. And the one interesting thing is that the proving of the invariance is very trivial in this sense. Now, if you take, if you see that translation generator del by del theta bar on LAC is same as d by dt of. Okay. So if you just translation along the anti-chiral direction is same as acting of the symmetry S1 and S2 corresponding ordinary Lagrangian here. And this also provide a proof of the fermionic nilpotency of the fermionic symmetry. Suppose you have, because these translation generators are nilpotent, if you apply del by del theta bar once again here and del by del theta here, it turns out to be 0 because of the nilpotency of the Grassmannian variables. So you can also capture the nilpotency of this fermionic symmetry in a very straightforward manner by using the translation generators. So let me conclude my talk. We have shown that by taking the superposition of superpotentials, we find that in that case we have two fermionic symmetry in each case and one bosonic symmetry, and the anti-commutator of these two has a discrete symmetry theory. And we have seen that there exists actually a couple of discrete symmetries which gives the correspondence to the Hodge duality operator of the differential symmetry. So it basically gives a proof of the conjecture which is already posed by Malik and collaborators way back. Though we have taken a case of the superposition of the superpotential, but can prove it at least in that case also. And these, whatever the on-cell symmetries we have the achieved fermionic and symmetries derived with the help of super variable approach, chiral and anti-chiral super variable approach. We derive these symmetries here, and the nilpotency of these fermionic symmetries is captured with the help of the translation generators in a very straightforward manner. Thank you.
Thank you very much for a nice talk. Any questions? I don't see any questions, so thanks again.
Thank you.
And we will move to the next talk.
Hi, can you hear me?
Yes, Yeah, we can hear you.
Okay, so
can you
start.
please
Yeah, sure. Okay, can you see my slides?
Yes. Okay, great. So the next talk will be, just wait a second. Yeah. So the next talk will be by Jakub Boschmera, and he will talk about effective actions from string field theory. Please start.
Okay. Hi, many thanks for the introduction, and also thanks to the organizers for giving me the opportunity to present this talk. So as you can see from the title of the talk, the main, so to speak, playground will be the area of string field theory. This is a quite a narrow area of research, even within string theory. So I will try to stay as much down to earth as possible in order to facilitate our results to a broader audience. So as you will actually see, most of the results which will be presented are actually applicable to quite general classical field theories. So let me start by briefly outlining the main objectives. So we want to focus on deriving T-level effective actions from string field theory. So here you already notice that I put the word string in a parentheses. So as you will see, many of the results will be indeed applicable to general field theories. So I would like to draw attention to the word 3 level. So we will stay at a pure classical level. So as you may know, within the context of string theory, this is still quite non-trivial because for general string backgrounds, we have an infinite number or infinite tower of states. So usually we just want to focus on the effective physics of a finite number of them. Usually the massless modes will do, right? So it's still quite non-trivial to basically get rid of the rest of the basically infinite number of states which are present. So next we will focus on the algebraic structure of both the parent UV string field theory actions, as well as on the algebraic structure of the derived effective actions. We will see that this is given in terms of the so-called strongly homotopy matrix and Lie algebras, which go under the name of infinity and L infinity. And we'll observe an interesting phenomenon that the algebraic structure of the parent UV theory gets transferred via the so-called homotopy transfer onto the effective theory. So in the very last bit of my talk, basically one of the last slides, I will also say a couple of words about the actual evaluation of the effective couplings for string field theory actions. So you'll see that in general this is quite hard because it involves computing in general offshore amplitudes, offshore superstring amplitudes at general momenta. But in the case we deal with a superstring with a global worldsheet unequal to superconformal algebra, and also at zero momentum, that is, we will only consider algebraic couplings of the effective theory, you'll see that there is a huge simplification which goes by the name of localization. So first of all, I intend to give a short introduction into string field theory and also into the field of homotopy algebras. And in the second part of the talk, I will focus on the effective physics. So
String field theory can be characterized as an offshell formulation of string theory, such that on shell, its phylum diagram expansion reproduces the first quantized string theory. So why do we do string field theory? So first of all, as it was recently shown by Ashoksan and collaborators in a still continuing series of very nice papers, it gives us a consistent treatment for dealing with string perturbation theory. Secondly, classical solutions of the string field theory action provide us with information about non-perturbative string backgrounds. So for instance, in the case of open string field theory, these are the D-branes, which you may have heard of course. And last but not least, it also provides us with a consistent approach of dealing with time-dependent phenomena in string theory. So what I have in mind is especially dealing with instabilities and the time evolution of string backgrounds during decay of such vacua. So for instance, we can have a look at this paper by Ashoksan dealing with the so-called throwing tachyon. So when it comes to the algebraic structure, this is something which I have already mentioned. So this is given in terms of the homotopy algebras. In the case of open string, we speak of the so-called cyclic or at a quantum level, quantum infinity algebras. In the case of the closed strings, we have L infinity. So in a moment, we will see what these algebras look like. As for the analytic structure, so this is something which I will try to suppress in this talk. As I was trying to already convey, I will focus mostly on algebraic structure, which is kind of transferable to general field theories, as we will see. But in general, the vertices of a string field theory action are given by two-dimensional worksheet vector plus Go CFT correlators, which are integrated over the moduli space of Riemann surfaces with punctures. So these represent string insertions, boundaries in the case of open string, and also genus when we go quantum. So let's now forget about physics for a while and focus on mathematics. So starting with the so-called infinity algebras, which were introduced by Jim Stashev in 1963. We will consider a graded vector space H. And on this graded vector space, we will have a set of products, mk, for each positive integer k, which are odd under the grading of the vector space, and they are also multilinear. So we will say that these products satisfy relations of an infinity algebra when the following is satisfied for some elements A1, A2, etc. of the graded vector space H. So the first relation tells us that this product M1 is nilpotent. The second relation is nothing but a graded Leibniz identity. The third relation tells us about the failure of the two products to be associative. So you can see that if, for instance, we would put M3 to 0, then this would give us basically graded associativity relation for M2. But in general, this is not the case. And we will say that M2 is associated after homotopy, which is given by 3. So more compactly, we can express these relations in the following way. In order to be able to use these infinity algebra to construct field theory action, we also need a mapping to complex numbers, which is provided by the graded antisymmetry or so-called symplectic form, which you require to be cyclic. Again, this is given by the following property. And provided that all these properties are in place, we can write the following action where phi is our dynamical field. So varying this action and using the cyclicity property of these products with respect to the symplectic form, we can derive the equation of motion, which is also called in mathematical literature Maurer-Cartan equation, which has the following linearized gauge symmetry. So now let me briefly talk about the L-infinity algebras, which are very similar to their L-infinity siblings, but in this case, the products, again, which are defined on a graded vector space, are graded symmetric. Sorry, there is a typo. So what I, of course, meant to say is L-infinity relations. So again, L-infinity relations closely mimic the structure of the infinity. So again, L1 requires to be potent. Secondly, we have the graded Leibniz. And instead of requiring associativity up to homotopy, we require Jacobi identity for L2, again up to homotopy. So in a close analogy, we can also write an field theory action with an L-infinity structure. Again, there is a typo here, sorry, this Q should be L1. Given an infinity algebra, what we can do, we can define products LK by graded symmetrizing, and it is an easy exercise to show that these graded symmetrized products satisfy the axioms of an infinity algebra. So means that given an infinity field theory action, we are always able to write it in an L-infinity form by graded symmetrizing the vertices of the action. This is something which I was already heavily hinting at. This L-infinity structure of field theories is not restricted to string field theory. In fact, a couple of years ago, Olaf Holm and Barton Zwieback conjectured that that any classical field theory can be rewritten in an L-infinity form. So here, in general, the vector space decomposes into the following graded components, where, for instance, H plus 1 is the space of gauge parameters, which can be empty. So we are not restricting ourselves onto gauge theories. We're trying to be indeed as general as humanly possible. Then H naught denotes the space of dynamic fields, and then H minus 1 the space of field equations, etc., etc. So we can really take any example of classical field theory which we like. So for instance, we can take mass of scalar. Then the L-infinity structure is given by L1, just the box operator, L2 and 3, etc. Will be given by the Taylor expansion of the scale potential. Okay, then of course we can consider, for instance, Chen-Salmon's theory. So here we have slightly more refined structure, the so-called A2 structure, which is nothing but a truncated infinity structure. So the kinetic operator is given just by the exterior derivative, and the M2 product is just a wedge product. Then of course we can, as I was saying, take whatever we like, Young-Mills, Einstein, Hilbert, and eventually we always find that the theory can be given an L-infinity structure. From the realm of string field theories, a particular simple example is de Witten's cubic string field theory, which is algebraically identical to Chen-Simon's theory. So here the kinetic operator is given by the BRST charge, and the two product is given by the Witten's star product. So although it may look very simple and easy to deal with such a theory, the very complicated nature of the star product makes it actually quite rich and interesting. So now let me come to the second part of my talk, where I will focus on the effective physics. So in order to set things up, let me start by considering a projector, which with respect to a symplectic form satisfies the following property. So, okay, let me also say that in this part of my talk, I will focus on infinity structures, but most of what I will say, indeed, the majority of results are easily transferable also to infinity. So using this projector, we will split our string field or dynamical field, whatever, in the following way. So little phi will denote degrees of freedom which we want to keep in the theory, and capital R will denote the degrees of freedom which we want to integrate out. In order to integrate out the degrees of freedom capital R, we define an operator on the space of fields, which we call a propagator, and can be used to integrate out these degrees of freedom encoded in capital R, basically using this algebraic property which is satisfied and which is usually called the abstract Hodge-Quadratic composition. Apart from this relation, we also need to satisfy a consistency relation, usually called annihilation or side conditions, which can be expressed in the following way. So now as for the actual integrating out, so what we do, we write down the equation of motion for the component R, which is given just by the p-bar projection of the full equation of motion, and we solve it for R in terms of lowercase psi. So psi, remember, encodes the degrees of freedom which we want to keep in the theory. So doing this, we obtain the following recursion relation for capital R as a function of lowercase psi, which can be solved in the following way. In terms of the interactions of the theory, so M2, M3, remember, are the infinity products which encode interactions, and of course the propagator H. Here we notice an important thing, namely that any gauge constraints which are connected with fixing the gauge for the degrees of freedom which we want to integrate out. So here I forgot to emphasize, we fix the gauge by requiring that H times R is equal to 0. So we notice that any potential gauge constraints are automatically trivialized. That is, if we consider a classical solution of the equation of motion for the degrees of freedom which we want to keep in the theory, this solution automatically extends to a solution of the full equation of motion. So if we then look at the effective equation of motion which we just obtained, we notice that it can be again organized into a manifest Maurer-Cartan form with a new effective products which are again infinity and are given in terms of the original UV products, the projector, and also the propagator in the following way. A general order, the structure of these terms is simply given by tree-level Feynman diagram expansion. You can also show that provided that the original infinite products were cyclic, then also the effective products are cyclic, provided that the propagator satisfies the following property with respect to this form. Finally, the effective action can be simply obtained by substituting the solution for integration out of massive degrees of freedom into the original UV action, and can be again expressed in manifest infinity form in terms of these new products. So let me now focus on the details of the algebraic structure of this procedure of integrating out of degrees of freedom. So again, let me forget about physics for a moment, and what I want to consider is a chain complex equipped with a contracting homotopy satisfying this generalized Hodge-Quadratic composition, as well as the so-called retract and annihilation conditions given by these relations. So this kind of algebraic structure can be altogether schematized as follows, and it's called a strong deformation retract. As an example, we can remember we can remember the algebraic relations satisfied by the quantities which we've seen in the case of effective theories, and we can notice that we have the following strong deformation retract. So given a strong deformation retract, we can ask ourselves what happens if we perturb the differential of one of the chain complexes in such a way that we again obtain a differential. And what happens is that we obtain the new SDR where the perturbed data of the strong deformation retract are given by these relations. This is something which is called homological perturbation lemma. So as you may notice, the SDR which we had on the previous slide, which pertains to integrating out degrees of freedom in an infinity field theory. There we have just a kinetic operator as our differential. So what we want to do is want to view the perturbation, the homological perturbation, as adding interactions to the theory. However, in order to do that, we somehow need to modify the notion of our infinity products because we just cannot simply add M2 to M3. To M4, etc., because they take a different number of inputs. So this is provided by the so-called tensor trick, where we go to the so-called tensor coalgebra, and we uplift the various maps which we had on the simple Hilbert space to maps on the whole tensor coalgebra. So I give just some examples of how this uplift works, but details are not important. So what is important is that starting with the uplift of the SDR, which I've already shown on my previous slide, which is basically given by a free theory, that is by the kinetic operator without any interaction. Then we can introduce interactions by adding these M2 and 3 uplifted to the tensor coalgebra, and running the machinery of the homological perturbation lemma, we obtain a new strong deformation retract, where after integrating out, we noticed that the formula provided by the homological perturbation lemma for the effective products exactly matches the effective products which we obtain by solving the equations of motion for the massive degrees of freedom. So generally, we can conclude that the homological perturbation lemma automatically takes care of the tree-level Feynman diagram expansion. So I just want to present one of the applications of the machinery which we've just developed, and this is for the so-called sequential integrating out of degrees of freedom. So first of all, we integrate out degrees of freedom given by one kind of a projector. Then subsequently, we want to refine this procedure by integrating out even more degrees of freedom. So either we can do this, we can perform this procedure one after another, or we can use the so-called composite propagator to perform this integration out in one go. So as an example, from the realm of open string field theory, formulated on a stack of DP branes, which should give us a non-abelian angles plus, of course, the alpha prime corrections. So we can first integrate out all massive modes using the Siegel gauge propagator. But what we are left with are not physical modes, I mean the gluons, but gluons plus the so-called Nakana-Shirl-Schrupp field. So in order to obtain an action for physical fields only, we also want to integrate out this Nakana-Shirl-Schrupp field, which can be done using the so-called algebraic propagator. Or we can do this, as I was just saying, in one go using the composite propagator. So on my final slide, I would like to briefly talk about the actual evaluation of the effective coupling. So up to now, I was only talking about purely algebraic manipulations, but what remains to be done is actually evaluating the couplings of the effective actions for general string field theories, that is computing some offshore tree-level string amplitudes, which in general turns out to be very, very hard. So in order to simplify, in order to actually have any hope of achieving some particular goals, so we will restrict ourselves on massless modes at zero momentum, which will therefore give us algebraic couplings, and which will therefore determine the moduli space or vacua for the background at hand. In order to simplify even further, we will focus on the superstring and on such superstring backgrounds which have global worldsheet unequal to superconformal field superconformal symmetry. So there is a conjecture formulated over the past 2 years, is that the computation of trivial zero momentum effective superstring couplings for such backgrounds with global unequal to worldsheet superconformal algebra actually localizes on the component of the boundary of the bosonic worldsheet moduli space, which is given by one propagated degeneration. That is on such a component of the boundary of the worldsheet moduli space where one of the propagators becomes infinitely long. So, there is, at the moment, there isn't a general proof of this conjecture, but there are a couple of hints that this indeed might turn out to be true. So, first of all, this was verified for quartic effective potential in open string field theory by McAfee and Baruano. And in general, as I was saying, this gives us, this computation should give us a structure of the moduli space for the given background at hand. So for instance, taking the D3, D-1 D-brane background, this indeed gives us generalized ideation constraints, as you would expect, because this is precisely a representation of n equal 4 superanimals instantons at the leading order alpha prime level. So in general, you would expect some alpha prime corrections, and indeed it would be very interesting to pursue this direction. So subsequently, this was also verified in the context of heterotic SFT. So in particular, this gives us the localization paradigm gives us that there is no need for actually defining, for actually working with an explicit formulation for a closed string free product, which is a huge help. And recently, this is still work in progress with Karol McAfee. The conjecture has been verified for certain 5-point couplings in open string field theory. So I will just flash the summary of my talk, and thank you for your attention.
Thank you very much for a nice talk. Any questions? So I have a question. So how hard is to calculate, let's say, 4.3 level open string amplitude? Has it been done using?
So you mean off-shell at general momentum? Okay.
Yes.
So so off-shell, there is a huge problem with worldsheet geometry. So for instance, if we work in Siegel gauge, then just to deal with the worldsheet geometry, we have to work with general Schwarz-Christoffel maps, which it can be done, and indeed it was done by people at the end of the 80s. So especially you should have a look at the papers by Giddings. But in order to actually evaluate this for particular, evaluate these amplitudes for particular backgrounds and general momenta, yeah, I think it cannot be done in general. I think maybe for some special choice of backgrounds, it can be done. This whole thing simplifies immensely if we go on shell. So if we go on shell, there is a nice result by Nathan Berkowitz and Martin Schnabel for 2003, which allows us to basically pull through the computation in general. So off-shell at general momentum. Yes?
Yeah, can you turn then the on-shell calculation in the actual worldsheet integral from this formalism?
Yes. So the on-shell calculation, it can be easily mapped onto the correlator on the upper half plane, and for instance, for the 4-point function, the integral is just integration over the Schwinger parameter of the propagator, and it's very easy.
Mm-hmm. Okay.
But for the offshore, yeah, there is this main problem with mapping the amplitude on the upper half plane, which involves these Schwarz-Christoffel maps, and most of these kind of guys are defined implicitly and cannot really be done analytically.
Mm-hmm. Okay, thank you. Okay, any more questions? If not, thanks, speaker, again. And we will have now a break and reconvene at 11:30.
To já myslím, že tam jak není prostě. Mr. Chairman, are you there? Ah.
Yes.
Okay, okay, you are here.
Yeah, it's still a few minutes left. Yeah.
Okay, now listen, I am old and unexperienced with this high technology. So you say some words and then I share the screen, put it on the whole screen and start, right?
Yes. Mm-hmm.
And should I now unmute?
Not yet, because
okay, you did not start.
Yeah, it's not once this screen disappears, the session starts, and then you can share your screen.
Yes.
Yeah, in few minutes. Yeah.
Okay, perfect. So I stay muted, but will be silent, correct?
Yeah, you then unmute yourself when you start. Yeah. Mm-hmm. Okay.
Jsem dneska slyšel pěkný. Co to tam bylo ve těch renormalizacích, takový prapodivný tok? Tam počítali něco v X reprezentaci nějaký nedělali. Jenom prosím, kdyby náhodou.
Okay, so we will start the next session. So Dmitry Hoshek is the next speaker. Can you please share your slides now?
That disappeared now.
There should be a green button which says share screen.
There is no share screen. I don't see the green, this disappeared simply. Oh, now it is okay.
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 Okay, great. So, so the next talk will be by Professor Hoshek, who will talk about predictive electroweak gauge model with strong spontaneous symmetry breaking dynamics. Please start.
Thank you. So, dear colleague, welcome in my office in Rzesz. and I will present the electroweak gauge model in which the weakly coupled Higgs sector is replaced by a strong spontaneous symmetry breaking dynamics. The last paper is written together with Petr Beneš and Adam Smetana from the Institute of Experimental and Applied Physics in Prague. Our argumentation is standard. There is nothing wrong with the Higgs mechanism as the origin of particle masses in a standard model, except first, it is certainly incomplete because the neutrinos are massive, because there is the dark matter, and because in a good quantum description, the fermion masses should be calculable. Second, the Higgs mechanism is perhaps phenomenological. That was pointed out already by its fathers. This means that the Higgs field is the fermion-antifermion composite, which necessarily needs a new strong force, but that is exceedingly difficult to handle. We defend ourselves by the Jesuit credo, which we know from a writing by Frank Wilczek. It states, it is more blessed to ask forgiveness than permission. Our basic references are more than 40 years old. Heinz Pagels and collaborators cleverly analyzed consequences of an unspecified strong dynamics, which they call quantum flavor dynamics, and they conclude that the fermion masses, or more precisely, the fermion self-energies, should be finite and calculable, because symmetry forbids the counter terms. Second, the fermion masses dynamically generated obviously breaks spontaneously the electroweak symmetry down to unbroken U1 electromagnetic. Consequently, there are just 3 composite would-be Nambu-Goldstone bosons, which give rise to masses of W and Z. And finally, there should be the composite Higgs particle as a symmetry partner of these composite would-be Nambu-Goldstone bosons. We take the liberty of using the name quantum flavor dynamics also for our particular strong dynamics. I remind that there are famous heuristic prototype examples of this reasoning. These are the famous papers by Bardeen, Hill, and Lindner, and similar paper by Miransky, Tanabashi, and Yamawake. For us, the key reference is the paper of Tsutomu Yanagida from '79. He gauges the flavor SU3 or family or generation or horizontal symmetry, puts all standard model chiral fermion fields into triplets, and the sacred anomaly freedom forces him to enlarge the fermion sector by 1 triplet over the right-handed neutrinos. Now, if such a gauge symmetry does exist at all, it is the firm experimental fact that it is completely and badly broken. Because it is a gauge symmetry, it must be broken spontaneously. And for that reason, Yanagida introduces a rather extended, weakly interacting Higgs sector with 2 vastly different mass scales. In conclusion, and here I quote, Tsutomu Yanagida suggests, the model is a possible candidate for the spontaneous mass generation by dynamical symmetry breaking, having in mind the famous Nambu-Yonah-Lasinio idea. Our task is to realize as honestly as possible this suggestion. Well, first I should emphasize that the attempt is immodest, if not nasty, because there is just 1 free parameter in the whole gauge scheme, and this is the theoretically arbitrary scale of quantum flavor dynamics. The rest are notoriously known electroweak parameters. So I start by describing the steps, first in words, and the violet abbreviates the degree of reliability. So in the first step, we will demonstrate that the strong coupling Schwinger-Dyson equation of quantum flavor dynamics generates spontaneously, that is in solutions, in a separable approximation for the kernel, 3 Majorana masses of right-handed neutrinos of order lambda and 3 Dirac masses of the standard model fermions, which are degenerate in given flavor or family, but they are exponentially small with respect to lambda. Experts immediately recognize that it is not surprising that Yanagida is co-father of famous ideas, seesaw, and the model of baryogenesis via leptogenesis, because you recognize immediately that there should be the seesaw in such a scheme. However, because of the strong coupling, there is the large theoretical uncertainty. The second step, I think, is waterproof because the existence theorem of Goldstone implies masses of all flavor gluons of order lambda and masses of electroweak bosons of order of the standard model fermion masses, which is in fact the induced Fermi scale. So that is very convincing step. The third step is hopefully plausible because we use the old Nambu-Ioannolassino idea and state that the symmetry partners of the composite would-be Nambu-Goldstone bosons should be the composite genuine Higgs particles. Finally, we attribute the standard model fermion mass splitting in given family to new sigma-dependent vertices which necessarily emerge in the electroweak Ward-Takahashi identities. That step we think is natural, elegant, but very fragile, as we will see in the following. So in formulas, step 1, dynamical generation of Majorana and Dirac masses amounts to solving the Schwinger-Dyson or gap equation. I remind that the fermion mass or self-energy is the bridge between the right-handed and left-handed field, and also what is very important, that in the non-abelian gauge theory, the vertices in the infrared are entirely unknown. Now the Majorana bridges are the bridges between the right-handed neutrinos and between the charge conjugate right-handed neutrinos, which are, of course, the left-handed fields. Group theoretically, it means that because of the Pauli principle, the neutrino mass matrix sits in the complex sextet, which is symmetric representation of SU3. The key point is that because of this decomposition, the hard Majorana masses are strictly prohibited by quantum flavor dynamics because there is no unity in this decomposition. Dirac bridges of the standard model fermions are the general 3x3 matrix which sits in this decomposition that is either in singlet or in octet. However, the hard Dirac masses are strictly prohibited, all of them, by the electroweak symmetry. Don't forget that the left-handed standard model fields transform as doublets. The doublet index is omitted here for simplicity. Now, because all fermions transform as triplets, the Dirac mass is identical for all fermion species in given family or flavor. Ultimately, they should be the calculable multiples of lambda because there is no other parameter but lambda. This is like the hadron masses in QCD in the chiral limit should be the calculable multiples of lambda QCD. So how do we proceed technically? We make Wick rotation, we fix the external momentum, we integrate over angles, and integrate over momentum only up to lambda, at which the coupling becomes small, and set the known asymptotically free small coupling to 0, and the model thus becomes not asymptotically but strictly free above lambda. This is the resulting one-dimensional Schwenker-Dyson equation. The kernel, however, remains completely unknown. For that, we make the BCS motivated separable ansatz of this form. Now, GAB are the effective low energy constants, and in the denominator, there is the product of one-dimensional momenta P dot K, and because of that, this integral equation is immediately solved because P goes in front of the integral. The difficult part is to solve the nonlinear algebraic equation for the matrix structure. If we neglect the flavor mixing, we obtain as the solution the following, that the masses, Majorana masses, are proportional to lambda. This number is quite random because one should need some experimental datum, whereas the Dirac masses of the standard model fermions come out exponentially suppressed with respect to lambda. Steps 2 and 3, first for the Majorana masses of the right-handed neutrinos. So it is not difficult to show that the Majorana masses break spontaneously the symmetry SU3 times U1 of the sterile neutrino sector at the scale lambda completely, which means that there are 8 would-be Numble-Goldstone bosons, consequently 8 massive flavor gluons with masses of order lambda, and 1 pseudo Nambu-Goldstone boson correspond to the anomalous global U1. These guys are seen as the massless poles in the Ward-Takahashi identities. What is extremely important that these would-be Nambu-Goldstones are both scalars and pseudo-scalars. That is, we are breaking spontaneously the chiral symmetry in this sector. Now, as I said already, these Nambu-Goldstone bosons belong to the composite complex sextet of SU3 times U1, but because 12 is 1 plus 8 plus 3, there should be in the spectrum 3 super heavy genuine Higgs bosons chi-I, composed of the right-handed neutrinos. The same steps for the Dirac masses. So we write down the diagonal 3 by 3 Dirac matrix as a linear combination of unit and diagonal matrices lambda 3 and lambda 8, and first discuss M0. M0 is obviously allowed by SU3 symmetry itself, but as I said, it is strictly prohibited by the electroweak chiral symmetry, which it breaks spontaneously down to U1 electromagnetic Bagels. Hence, there are 3 would-be Nambu-Goldstone bosons, hence W and Z. I will show how this is done very quickly in a minute. These would-be Goldstones are visible as massless poles in the Ward identities. I will show explicitly later these identities. As in the standard model, these guys sit in the multi-component complex doublet, and because 4 is 3 plus 1, there should be in the spectrum 1 Higgs boson H at the Fermi scale, composed of the standard model fermions, but that is a necessity because such a particle has been discovered at LHC. So this is a mandatory postdiction. The same for M3 and M8. It is obvious that M3 and M8, which sit in octet, break SU3 in the standard model sector down to unbroken U1 times U1. Hence, there are 6 would-be Nambu-Goldstone bosons made of standard model fermions. But because 8 minus 6 is 2, there should be in the spectrum two new Higgs bosons H3 and H8 at Fermi scale, composed of the standard model fermions. These are bona fide reliable predictions of the model. And I should mention that Peter Higgs the Great already in his seminal Abelian paper in '64 mentions in 2 sentences that, of course, I mean, that should, the Higgs mechanism should work also for the non-Abelian gauge theories. Everybody knows that for SU3, the gauge fields transform according to octet, and he explicitly used the octet for the Higgs fields and comes exactly to this conclusion. Now, for this argumentation, I have switched off completely the electroweak interactions, but M3 and M8 break also the electroweak symmetry. So there should be some small additional contributions. This deserves further study. I expect a mixing of X's. Finally, the step 4, what are the effects of the chirality changing self-energy for the electroweak observables? Because there are new vertices of fermions with electroweak gauge bosons enforced by Ward-Takahashi identities. So don't be afraid of these formulas in the frame. This is the photon W and Z vertex in addition to the standard electroweak vertices. There are the contributions for sigma. First, notice that in the axial vector channel for W and Z, there are the famous massless Nambu-Goldstone poles with derivative couplings to the fermions, and the self-energy comes in the sum. So even for constant sum, there is the contribution, like in the Nambu-Nalassino model. The influence of the vectorial vertices is more subtle because it depends basically upon the derivative of sigma. That is, it has to be the momentum dependent. This vertex, in this contribution to the photon vertex, is known in the literature as the Ball-Chiu vertex. But I must say that that vertex was known to Pagels and Stockar earlier and also employed in the context which I am going to present in a minute. So how do we use these new vertices, which are necessary consequences because the word identities are the consequences of the symmetry of the Lagrangian, not of the ground state. So first, and this is just a reminder, we use the axial vector Nambu-Goldstone vertices for computing the polarization tensor loops of W and Z. That was done first by Jackie and Johnson. Peter Benesch put his hands on this problem, and this is the standard part of the technical computation. If you know sigma, as we do, you can compute the pion decay constant, which basically actually gives rise to the mass of W and Z. And this is the famous Pagels-Stockar formula. It is easy to compute this integral with sigma equal m squared divided by p, and this is the result. And if you assume that you can saturate these sum rules by one mass, you get the estimate that the heaviest mass in the world, in this simplified world, where everybody is degenerate in given flavor, you get the number 390 GeV. So finally, we use the polar vector vertices, which are momentum dependent, for computing the fermion mass splitting. This amounts to computing these two integrals in the lowest order. And quite remarkably, that computation can be done practically without any approximation. And this is the result. But you might object, or I should say that these A and B are the explicit well-defined functions. Objections. How can it be that the weakly coupled electroweak interactions give rise to the observed huge mass top-bottom splitting? We say there is a hope because the fermion masses are given by solving the nonlinear pole equation of this type. And it, of course, depends crucially upon the functional form of the computed sigma. Second objection is, how can the electroweak interactions having the identical couplings for all three families produce mass splitting, which is definitely not identical for all three families? Remember that the up quark is lighter than down quark, whereas for second and the third family, this ordering is dramatically reversed. We say there is the hope because the formula contains the ratios fermion masses divided by masses of gauge bosons can be either smaller than 1 or bigger than 1, so this ordering can be perfectly changed. Unfortunately, the life is not sweet enough. The numerical solution of the pole equation yields only the small unrealistic fermion mass splitting. So I conclude, actually, I should say that what I have presented is rather a framework or scenario, because not everything is computed until the end. And first of all, we know no way of knowing whether this inequality is the inherent property of quantum flavor dynamics at strong couplings or not. If the assumption is valid, first, there is no generic electroweak Fermi scale, there is only huge lambda. Second, 3 active neutrinos are the very light Majorana fermions. Third, 3 super heavy Majorana neutrinos are quite useful for seesaw and for the leptogenesis, but what is important that they are on the same footing with other standard model fermions. From that, we speculate that whereas ordinary matter is made, the luminous matter is made of QCD nucleons QQQ, the dark matter might be perfectly made out of quantum flavor dynamic composites nu R, nu R, nu R. So the dark universe is fermionic. For calculation, in fact, postdictions of fermion masses is hampered by theoretical uncertainties. The neutrino masses are predictable in terms of the Dirac mass with corrections, electroweak corrections, and with these right-handed masses by the seesaw formula. 5, we postdict the composite Higgs standard model alike and predict H3 and H8 at Fermi scale, which illustrates that because we are dealing with quantum flavor dynamics, not all 3 families or flavors are alike, because these Higgses interact with fermions via lambda 3 and lambda 8. Finally, we don't ask forgiveness yet. Thanks for your attention.
Okay, thank you very much for an interesting talk. Are there any questions?
If I may have.
Question? Yes.
On page 5 of your presentation, there is a Schwinger-Dyson equation with brutal ansatz, separable ansatz for the kernel. So my question is whether, it's from times when people try to do that, there was some progress, typically with Philip Mannheim. And my question is, did he support this separable or something more complicated?
Well, actually, this is mandatory question. But I should remind you that in BCS, the separable ansatz is extremely weird because it neglects vast majority of interactions of electrons But it was argued many years later, I think 30 years later, by Polchinski, what is the reason for this separable approximation. I have no idea why this works. And the Philip Mannheim actually argues that this behavior of sigma 1 over p is a consequence that he would like to have the 4 fermion interaction renormalizer. So this is the product of result of playing with anomalous dimensions.
Thanks.
But I do not have any theoretical control.
Okay, thank you. If there are no more questions, thanks Professor Hošek again. And we move to the last talk of this session. So the last speaker is Anka Turenu. Please, can you share your slides? Great. And the topic is intrinsic quantum coherence in particle oscillations. Please go ahead and also you unmute yourself.
Good afternoon, and thank you. Do you hear me now?
Yeah, we hear you, but we don't see your slides now.
You will see them soon. Here they are.
Yes, yes, great. Okay. Yeah, let's start. Thank you.
Yeah. Well, it may come as a surprise for many of you, probably, that there are still standing problems in the theory of particle oscillations. And today I would like to give you a glimpse into one of these key problems, which is the quantum coherence. We know a handful of particle oscillation phenomena, and actually all of them have revolutionized the way we regard particle physics, or they have the potential to revolutionize this. We can divide them in two classes, so to say. One is the particle-antiparticle oscillations, and these are the first observed, the K0, K0 bar, and more recently also B0, B0 bar, D0, D0 bar. And in this paper of German and Pais in 1955, it was introduced perhaps for the first time the idea that particles can mix and oscillate. They are connected, these phenomena are connected, of course, with the famous CP violation in weak interactions. Still in the particle-antiparticle oscillation type of phenomena are the hypothetical neutron-anti-neutron oscillations, which are connected with baryon number violation, which is a key element for baryogenesis. And their study started in earnest in 1980s. They are still unobserved, but there are experiments which put some bounds on this neutron-anti-neutron oscillation process, and still new experiments being planned. And in another class are the so-called flavor oscillations, and here are the famous neutrino oscillations, in which electron neutrino can go to muon neutrino, for example, and muon neutrino to tau neutrino, or any other combinations. This type of oscillations were first introduced, actually the neutrino oscillations were first introduced by Pontecorvo in 1957 as particle-antiparticle oscillations, because in those times it was known only one type of neutrino. In 1962, Maki, Nagakawa, and Sakata introduced in earnest these flavor oscillations, because by then it was almost sure that there are actually two types of neutrinos. And in 1968, in this famous paper of Gribov and Pontecorvo, the flavor neutrino oscillations were used to explain the solar neutrino problem. And actually this paper, in which neutrinos are treated as Majorana particles, embodies our current understanding of the standard theory of neutrino oscillations. Later on, Bilenki and Pontecorvo introduced also the oscillations for the Dirac neutrino, or neutrinos with Dirac masses, so flavored neutrino in that case. Of course, at this moment, the neutrino oscillations are the stars of the show, due to the great activity which surrounds them, and not least due to the 2015 Nobel Prize in Physics, which was awarded for the discovery of neutrino oscillations. Of course, it is possible that if neutron, anti-neutron are ever observed, they will become instantaneously the superstars of the show. However, since we have at the moment neutrino oscillations as the cleanest, so to say, particle oscillations, neutrinos being elementary particles and being involved in only one type of interaction, namely the weak interaction, I shall refer further to neutrino oscillations. However, all the discussion can be applied just as well to any other type of oscillation, either of scalar particles or neutron, anti-neutron, or anything else. So in short, I will just give you an idea about the standard approach to neutrino oscillation, and motivate and explain what is the theoretical challenge which we are facing with respect to the coherence, the quantum coherence phenomenon. And then we will look at some quantum mechanical systems which may give us a hint about how to solve this, this problem. And we shall come to my proposed solution to defining intrinsically coherent oscillating particle states in the case of neutrinos. But as I said, this can be enlarged to any other type of oscillating particle phenomena. And in the end, we shall look at what should be done and what, how the works can continue in the future. Well, the standard theory of neutrino oscillation starts with a Lagrangian with flavor violation for the neutrinos. Here I am going to speak all the time about the two neutrino models, because everything can be straightforwardly generalized to three neutrinos. So this will keep it simple and to the point. So we have a Lagrangian with flavor violation. This part, actually the non-diagonal terms in this matrix represent the flavor violating terms. And we have Dirac neutrino masses, which can be easily introduced in the standard model by adding Yukawa terms for neutrinos. What we do usually is to take this Lagrangian, which is seen as a classical Lagrangian, and diagonalize it. This is a solvable problem. in field theory. So diagonalization is achieved by rotation, a unitary transformation of these so-called flavor fields into these psi1, psi2, which are the so-called mass fields, with the rotation angle given by the parameter in this mixing matrix, in this mass matrix. And upon this change of variables, we come to this form of the Lagrangian, which is the Lagrangian of two free massive fermionic fields. We call them massive neutrino fields. Now, this is trivial to quantize, and we do it canonically. And in this case, the massive neutrino fields are expanded in these modes. Creation and annihilation operator for neutrino and anti-neutrino, yeah, because we have Dirac neutrino masses. And in this case, the massive neutrino states can be immediately defined. We have phi 0 as the physical vacuum, the vacuum of this Hilbert space. And this is a neutrino, one neutrino state, and this is a one anti-neutrino state. So this is all very simple. Now, once we have diagonalized the Lagrangian, these flavor fields have disappeared. So what oscillates then? What are the states that oscillate? Please take note of the fact that these flavor fields are interacting fields. And for them, we cannot define creation and annihilation operators. So we cannot define flavor states, flavor neutrino states associated to these flavor fields. How do we describe then the electron and muon neutrinos? Because they are supposed to go into each other. So how do the oscillation happen? Well, this is what Pontecorvo introduced as a conjecture, actually, and it has remained as a conjecture. Pontecorvo says that there exist flavor neutrino states, which are expressed as coherent superposition of the massive neutrino states, nu1 and nu2, with different masses, very important. And how these coherent superpositions are formed is by exactly replicating the mixing formula for the fields. So what we had before for flavor neutrino fields going in by change of variables to massive neutrino fields, we will have for the states as well. In that case, oscillations can take place. Namely, if we start with electron neutrinos and let them evolve, after some time we can find the non-zero probability that they would manifest themselves or exist as muon neutrinos. And this probability is what oscillates. This is why we call them particle or neutrino oscillations in this case. So the oscillatory factor here depends on the mass square difference between the two or the three neutrinos in the usual case. This formula is obtained in the ultra-relativistic limit, and here you have the graphical representation. So if we start with a bunch of or a flux of electron neutrinos and let them propagate freely, the probability to detect them as electron neutrino goes down, and the probability to detect them as muon neutrino goes up in time, and so on, and the phenomenon is oscillatory. So the requirements, in short, for neutrino oscillations are to have a flavor violating Lagrangian, of course, because we need to go from electron to muon neutrino, for example. We need to have massive neutrinos because the oscillatory factor was depending on the difference of masses, yes. And essentially, as in any interference phenomenon, we have to have the flavored neutrino states represented as coherent superposition of massive neutrino states with different masses. And here I am mentioning that they belong to different Fock spaces. Yes, the different mass particles belong to different Fock spaces. This is a crucial point in the following. However, if we think about quantum field theory and about production of particles by relativistic quantum field theory processes, the particles with different masses are always produced and absorbed incoherently. Yeah, if we have a final state with different masses, then there is absolutely no relation between those particles of different masses. So somehow Pontecorvo's conjecture is conflicting with what we know from usual conventional quantum field theory. There have been many attempts to incorporate this oscillation phenomenon into quantum field theory. And here is a brief, very brief list of what I consider the most important works and the most ingenious works. However, in all these works, the Pontecorvo flavor states could not be obtained as written exactly as they were written by Pontecorvo and Gribov and so on and so forth. And also another element which is missing from all these trials is the coherence. So including naturally coherence of the flavored neutrino states in conventional quantum field theory is not possible. It can be postulated, of course. It can be said that at t equal to 0, two neutrinos of different masses are produced. However, the theory does not support such an interpretation. So let us see from where we can derive some inspiration for a consistent formulation of the flavor neutrino states. And we shall look at some quantum mechanical processes in which coherence is inherent. The prototype of quantum oscillation are the two-level quantum systems. And many times you probably hear that neutrino oscillations are actually modeled as a two-level quantum system. You will see soon that this is actually not the case. These are quantum mechanical systems with two stationary states described by a Hamiltonian, which we'll call H0, with two basis states, 0 and 1. Now, we can include interaction. And in this case, the basis of stationary states changes. Of course, the stationary states of the new Hamiltonian are different. And we can start to look at the oscillation phenomenon in this two-level quantum system in the following way. We take a time t equal to t0, before which the system is prepared in a stationary state of H0, in the stationary state 0, let's say. And the system has evolved with the Hamiltonian H0. Then at t equal to t0, we turn on the interaction suddenly. This is extremely important. Then the states do not have time to adjust to the new Hamiltonian. So the state of the system will remain this state 0. However, now the system evolves with the Hamiltonian H, and the state of the system is written as a linear superposition of the, or coherent superposition of the stationary states in the new basis. We let it evolve, and at the time t0 plus delta t, what we do again is to remove suddenly the interaction and determine the state of the system. Again, the system can be either in the state 0 or 1. It turns out that, of course, this is calculable, the probability to find the system in either of these states, and the probability of the system going from the state 0 to 1 is given by this, again, oscillatory factor, which is absolutely similar to Pontecorvo's formula. Now, we have to note that in quantum mechanics, this was quantum mechanics, where all the representations of the canonical algebra for a given system are equivalent. This implies the fact that if, these stationary states of H0 form a basis, and the stationary states of H, the perturbed Hamiltonian, form again a basis, and we can go between these two bases by a unitary transformation. They have the same ground state and so on and so forth. Now, the two bases are well defined, irrespective of the relation between themselves. And this coherent superposition of states can be achieved by turning on and off the interaction suddenly. This is how we obtain coherence here. Now the question is whether this simple quantum mechanical picture can be extended straightforwardly to particle oscillations, to quantum field theory. If we look at the case of the neutrinos, we see that the flavor violating part of the Lagrangian cannot be turned on and off at will. It is there and it stays there. Then this means that the coherence of the flavor neutrino states is intrinsic. It cannot be triggered by external factors. And actually we cannot have the principle of superposition of quantum mechanics, because the states which are superposed in this case belong to two different systems. Two particles with different masses, according to quantum mechanics, are two different systems. They are not the same system. So we can conclude that the quantum mechanical interpretation of neutrino oscillation is conceptually untenable, although the formulas look practically identical to Pontecorvo's formulas. So this cannot be a way for us out. Now there is another instance of coherence in quantum mechanics, and those are the coherent states in quantum optics. They are superpositions of infinite number of Fock states introduced by John Clowder and later on by Sudarshan and Roy Glauber. And you recall that there is a Nobel Prize to Glauber connected to these coherent states, and they're using quantum optics. Now, the coherent states are eigenstates of the annihilation operator, and here they are taken for the harmonic oscillator, the simplest case. This is the annihilation operator, it annihilates the vacuum, and this is the formula of definition, where alpha is a complex number. And if we require this relation to be fulfilled, then this state alpha, which is a coherent state, can be written as an infinite superposition of these states n, which are nothing else but particle states or Fock states. Of course, in this case, all the Fock states belong to the same Fock space. do we have a chance then to apply these ideas in quantum field theory? It is actually well known that in quantum field theory, the notion of coherent state appears as vacuum condensate. So infinite number of particles belonging to the same Fock space. What do we need for particle oscillation? We need coherent oscillating states which are formed of a finite number of particle states which belong to different Fock spaces. So we cannot go on that route either, but we can try to manipulate a little bit the things so that we come to some notion of coherent oscillating state in quantum field theory. And here is my proposal to define intrinsically coherent oscillating neutrino states. Whenever in doubt, it is good to return to first principles, according to which in quantum field theory, particle states are defined by the action of an operator on the vacuum state of the system. Now, we know what is the physical vacuum state. Yes, it is very easy to find it for that Lagrangian that we had before. We have to find the operator that will give us coherent states, coherent oscillating states or flavor states. So the idea here is to associate the flavor neutrino states that we are after to the actual flavor neutrino state, field of the standard model. But the flavor neutrino fields of the standard model are massless fields. Yeah. In other words, we have to connect massless to massive neutrino fields. This brings to mind immediately the Nambu-Yonah-Lasinio model for the dynamical generation of nucleon masses, and actually the technique is inspired by this model and by the Bardeen-Cooper-Schrieffer theory of superconductivity in Bogolyubov's formulation. So we will have quasi-particle Bogolyubov transformation and so on and so forth. The technique now is based on the diagonalization of the quantum Hamiltonian in contrast to what we had before, namely the diagonalization of the classical Lagrangian, yeah, in the standard theory of neutrino oscillations. So what we do is to calculate the Hamiltonian corresponding to the previously introduced flavor number violating Lagrangian. And here is the Hamiltonian, where we treat this these mass terms as interaction terms, actually. The diagonalization is done in Heisenberg picture. This is a classical technique, and it starts from identifying at a given time t equal to 0, and only at that time, the fields which appear in this Hamiltonian with some other fields which are actually the standard model massless neutrino fields. Yeah, these are not massless fields. They are, okay, some flavor neutrino fields with a flavor number violation. Yeah. Now we can expand these standard model massless neutrino fields, and we have creation and annihilation operators for them. We plug these formulas into the Hamiltonian using this identification, and we find a non-diagonal Hamiltonian in terms of the massless particles operators. We call them bare particles in the theory of superconductivity, for example. Here, this is the free part or the diagonal part, and this non-diagonal part is actually the result of those mass terms of the so-called interaction. Yeah, actually, they come from Yukawa interactions. The diagonal form to which we want to reach is this one here in terms of creation and annihilation operators of massive neutrinos with those masses that we had before M1 and M2. So the eigenstates of the diagonal Hamiltonian, these ones, are the physical particles. And in other words, the massive neutrino states are the physical particles or the Bogoliubov quasi-particles. In order to go from this non-diagonal form to the diagonal one, we are going to do two changes of variables. So first, we start with this massless neutrino operators, which are acting on a vacuum denoted by this zero, which is non-physical. And we will move to, by a simple rotation, to another set of massless operators, which are denoted here by A1 and A2. This is the first step of the diagonalization. And the second step is to go from this A1 and A2 massless operators to the massive field operators with masses M1 and M2. And that is done by a Bogoliubov transformation between massless and massive operators. It is, of course, the usual non-Bouillon-Lasignol technique here. All this is, of course, calculable in detail. And we find these coefficients of the Bogoliubov transformations. Now, in the new vacuum, the vacuum for these particles, which is written here as a physical vacuum because they are the eigenstates of the diagonal Hamiltonian, the physical vacuum appears as a condensate of Cooper-like pairs of massless neutrino and antineutrino, as it is written here. Yeah, and this is the relation between the non-physical and the physical vacuum. It is a coherent state. It is an infinite superposition of, or a condensate of Cooper pairs. If we look at the projection of the physical vacuum and the non-physical one, we find that in the infinite volume and infinite momentum limit, this scalar product of states is actually equal to zero. This means that the two vacua do not overlap at all. In other words, the Fock spaces built on the two vacua do not contain any common states. So this, in turn, is connected with Haack's theorem, and is actually a reflection of the fact that the Stone-von Neumann theorem from quantum mechanics is not applicable in quantum field theory. So in this interpretation, the massive neutrino states are seen as Bogoliubov quasi-particles. Yeah, they are the physical particles of the model. Well, it remains now to define the oscillating neutrino states. How do we do it? Now we have so many possibilities that it is very easy actually to find some fields to do the job. And here we have the massless state, the massive operators, which can act on the physical vacuum of the theory. So this is the proposal about definition of the oscillating neutrino states. We take the standard model massless neutrino operators acting on the vacuum of the massive states. We know how this action takes place, and we obtain here this formula for the electron neutrino, for example, which is identical to the Ponte-Corvo formula up to these factors here, which make the electron and muon neutrino not to be orthogonal actually anymore. So in this case, the oscillation amplitude is never zero. We will always find if you look here, even at t equal to 0, this amplitude is not equal to 0. And this means that there is always a portion of muon neutrino in the electron neutrino and vice versa. However, in the ultra-relativistic limit, in which all the experiments are done, one recovers, Pontecorvo's oscillation probability exactly as it was derived by Pontecorvo and many people afterwards. So to conclude, we have seen that the coherence of the flavor states are the key element for oscillations, and they cannot be implemented by the usual quantum field theoretical prescriptions. The proposal here is to construct intrinsically coherent neutrino states for oscillating particle states by establishing a one-to-one correspondence with the standard model massless neutrino states. This procedure can be implemented for any oscillating systems, and the quantitative differences can be significant for non-relativistic neutrinos. And here we may have some influence on the interpretation of the results of the Catherine or Ptolemy experiments in neutrino physics, and possibly for neutrinos propagating in matter, especially in extreme conditions like supernovas. Finally, this would be the first step towards elucidating the mechanism of interaction of these oscillating particle states, which is still unknown. Thank you very much.
Okay, thank you very much for an interesting talk. Any questions? Yes, here is the question. Adam Smetana, please unmute yourself.
Hello, can you hear me? Hello?
Yes.
Okay.
Yes, we can hear you.
First of all, thank you for this very nice talk. And I would have a question. When you are using this Nambu-Lasinio construction, this doesn't necessarily mean that you need dynamical mass generation as it is in their paper, right?
No, not at all. Actually, one takes, I will go to the slide. One considers here the effective mass terms, which are practically the same thing which comes in the Nambu-Lasinio as effective term. Yeah, from that 4 fermion interaction, it comes to a bilinear interaction. Yes. So in this case, the equivalent, so to say, of that interaction is the Yukawa interaction in the standard model.
Mm-hmm. So basically, it's applicable also to standard model with elementary Higgs, right?
It is, and actually it is applied here. It is applied to standard model with the usual Higgs.
Okay, thank you. And second question I have. Do you apply this construction also to say something about decoherence and decoherent length of the neutrino oscillations?
Well, coherent states remain coherent in the propagation if nothing happens, if there is no influence of the medium. So I would say that it is premature at the moment to say anything about decoherence, because we do not know how these oscillating particle states interact. So one has to elaborate a mechanism of interaction. How do we put them to interact with W and Z bosons? Yes, how do we produce them? Of course, there may be many problems related to this aspect. However, it is a first step because we have, at least we have some states. We know how to write coherent states. Now, it may the interaction of the coherent states in quantum mechanics, in quantum optics can give us some inspiration for this. However, at the moment, I cannot say much about it.
Well, I meant that I saw that the interactions with W and Z are just standard model-like, or they are supposed to be somehow different by this construction.
The interactions with W and Z are very clearly defined for the massive neutrinos. However, when we ask the massive neutrinos to bunch together as coherent states of neutrinos, as flavor states, the situation is not so clear anymore.
Okay, I see. Interesting. Okay, thank you very much.
Okay, more questions? If not, I would like to thank the speaker again and all the speakers of today's session. And this concludes today's session, and have a nice day.
Thank you.